All right, welcome everyone to the course GPU Programming with Julia. I'm very happy to have Tim here, of course. We will have a course of 2 parts. First part will be by myself, by him, and the second by myself. So Tim is somebody who brought GPU computing to Julia. He was the creator of CUDA.jl, or let's say of the previous packages before CUDA.jl, which in the end turned into a GPU compiler, the GPU compiler package plus CUDA.jl today. And yeah, so it's a great honor to have him here to give this course. And myself, I'm a computational scientist here at CSCS. So I've got to mention Tim works at JuliaHub now. JuliaHub is the company that was founded by the co-founders of the Julia language. Then we have as additional instructor for the exercises Till Aaron Gruber. So he will, during the exercises, also walk around and help you. Yeah, then organizationally we will today now start, right, 10:30, but the days afterwards we'll start at 9 and usually finish at 5, but let's say it's not so important how we organize the day. We will see how we do it. The important thing is we start at 9, right? That's the important thing to know. And we will have lunch at 12:30. Maybe today we will start at 12:30 with lunch. That's up to Tim to see how it goes with the time. Yeah, I think that's all for now, except one thing. So we have here already 2 posters outside hang up. We will have some brief introduction to these posters by the participants to show their projects on Julia at a good moment later. And if somebody else has still brought a poster, please hang it up afterwards at midday break. All right, so with this I give over to Tim. Thank you very much for being here.
Thank you for the introduction. Is this loud and clear? Sounds awfully loud. I'm going to switch to JupyterHub. Multiple screen, sidebar can go. So today and tomorrow I'm going to give an introduction on how to program GPUs with Julia. My part of the course is going to be fairly explanatory, and there's going to be some exercises at the end of each part, but I'm guessing that Samuel's part will contain a lot more exercises, so feel free to try and follow along. If there's any questions, feel free to interrupt me. I'll try to give some time at the end of each bit so that everybody can try and follow along and figure out what's working, what isn't working, and so on. Maybe I should zoom in a little more, and this can go as well. So today I'm going to focus first giving a brief introduction, then I'll be focusing on the different programming models that we have in CUDA.jl and more broadly in the GPU stack in Julia. I'll be explaining how you profile GPU applications, how you optimize them. And then tomorrow, the first half of the day, I'm going to explain some more detailed topics on memory management, on concurrent computing, and some low-level libraries for people who are a little more seasoned with GPU computing and want to figure out how to do things in Julia. Is this all legible font-wise, or do I need to zoom in a little more? Maybe in the back, a little more? There we go. So first of all, why consider using GPUs in the Julia language? So there's been plenty of talks on this on the different Julia cons and on YouTube, but very briefly, Julia is a high-level language, meaning that it's still convenient to write in such a language as opposed to some lower-level languages that can be daunting to some people. But at the same time, the language has been designed in such a way that it should still be possible to get to all of the performance. Emphasize on the should, it's still a high-level language, so there's always some trade-offs, but generally it should still be possible to acquire the level of performance you get in C and C++ or you get in CUDA-C. So that unique combination makes it a good language, and it is in part because we have a JIT compiler, meaning that at runtime we can generate code for exactly the things you ask the language to do. And that's a fairly unique combination, and it also makes it possible to create some abstractions that are more difficult in other languages, like these higher order abstractions that I'll be talking about. The course, however, is specific to CUDA.jl for a couple of reasons. And the most important one, of course, is that the supercomputer here has CUDA GPUs, but also because CUDA.jl is the most mature package. There's a couple of others, and crucially, they're nowadays all built on the same tool stack. So as Sam mentioned, we have CuArray, we have GPU compiler, we have packages like LLVM.jl, adapt.jl, and they all are the foundational layer for all of these GPU packages, which means that most of the things that I'll be explaining today, you can actually also try, say, on your laptop, if you have a Mac laptop with an mGPU using the metal.jl package, or if you have an Intel laptop with an IGP in your CPU, you can use oneAPI.jl. Or if you want to use a different supercomputer that has AMD GPUs, you can use AMD GPU.jl. Of course, a couple of things like the profilers and some optimization things are going to be CUDA specific, but the broad line, the broad approaches you can apply to all of the GPU packages we have out there. So I listed AMD GPU.jl, oneAPI.jl, metal.jl. There's a couple of others, and we have a homepage, JuliaGPU.org, which also has a blog you can subscribe to, because once in a while we write a post about the new features that the new release of all of our packages have. So that may be interesting to follow development without having to follow the releases on GitHub, which can be a little verbose. So for the setup, I'm assuming that all of you have followed the instructions on Slack and have access to JupiterHub with the configuration that gives you Julia 1.10. Is that an issue for anybody? If not, this would be the point to have a quick look at your system. All right. So then you can check out the notebooks for these sessions. They're at github.com/Mariot/CSCS 2023. You can check that out using the terminal, or check that out using the JupiterHub functionality. It doesn't matter. Just make sure that you're using the stripped branch, which is the branch where I've stripped the solutions. That is not a very secure way to do so, but that's also not my intention. So the main branch still has all of the solutions, but I recommend you to try and follow along and just not look at the solutions from an educational perspective.
Sorry to interrupt quickly. I see a few faces that are worried. So I guess you have all by now seen the Slack channel. And so there is a channel announcements and instructions. So there you find the instructions to get started with the JupiterHub. And most of you have done that. Maybe not everyone. Somebody not yet there. So what he was referring to before, that you will have Julia 1.10, is once you enter into JupiterHub as shown there, and you open a notebook, and and then you choose the kernel 1.10.
So to verify, if you open a new tab and then you start a terminal and then you do Julia, you should have Julia 1.10 RC1. All right, let's continue. So if everybody has access to the notebooks, we can actually start executing some of these cells. And one thing to note here is that because of how the cluster is set up, you can actually only ever have one notebook or even one process running on the GPU at the same time. Otherwise, you'll run into exclusivity device error. So you can see here at the bottom that currently I have 0 notebooks active. If you have multiples of these and they're actually using the GPU, you will be running into issues. So in that case, you can go to the sidebar and on the stop button, you can actually shut down kernels so that only one kernel is running. And this also applies to terminals that are using CUDA.jl. So at some point, you will be using a new terminal to profile CUDA. In order for that to work, you'll have to shut down the notebook and vice versa. When returning to the notebook, you'll have to shut down the terminal because you can, again, only ever have one process using the GPU. Once that's done, you can start by activating your first cell. Here I'm going to activate the Julia package environment that I have provided in the Git repository, which specifies which packages that are installed and readily available. Normally, in another environment, you would do this yourself by doing package.add CUDA, which is essentially the only thing that's needed to install a GPU backend. When you then do using CUDA, it will look at the driver that's available. It will install the necessary CUDA toolkit in your local Scratch directory. So it should all work out of the box fully automatically. The only thing that you need to have on your system is the NVIDIA driver. This will take a minute. In my case, it's only activating project because I've activated this project already beforehand. In your case, you will see a whole bunch of outputs, installing all of the necessary dependent packages, pre-compiling them, downloading artifacts, and so on. So this will take a couple of minutes. So I suggest firing this off and coming back in a minute. If there's any problems, raise your hand and we will come and take a look. Once that's finished, you can import the CUDA package, and you can then do CUDA.versioninfo, which is always a good smoke test when using CUDA.jl on a new system, because it will print a bunch of outputs based on the environment that it has detected and the artifacts that it will be using. For example, here we can see that we're using CUDA runtime 11.8, and that's because the driver that's provided by the cluster is version 11.4. The NVIDIA driver is listed as well, and then there's a whole bunch of libraries, which shows that CUDA.jl is more than just a programming framework. It's actually a full-fledged interface to all of the libraries that NVIDIA packages by default as part of the CUDA toolkit. There's actually a whole bunch of considerations here with regards to which packages you can and cannot use. So technically, it's possible to opt out of all of this magic and use a local toolkit by calling the CUDA set runtime version with the argument local toolkit equals true. That is sometimes required if you're, for example, using very recent hardware that's only supported by a CUDA pre-release that's installed locally on the supercomputer. Then you can do this, and you will see in the version info output that we're using a local installation. If you were to do this on pitfalls, you'd get selected CUDA toolkit 11.0, which is buggy and broken, so don't do this. Let's continue. Just putting this out here, if the local discovery functionality would not find all necessary components, you can actually enable a debug mode by defining the Julia debug environment variable, setting it to CUDA runtime discovery, which is a package that's responsible for picking up all of the CUDA pieces that are installed locally. And then you'll see when importing CUDA some debug information about which pieces it had found, where it is looking, what could be missing, which again may be useful if you're working on a specific cluster that needs you to use the local toolkit. Again, as I mentioned, CUDA is a fairly large package. So as part of this introduction, I'll do a very quick run through showing the functionality that we will be explaining more thoroughly in the coming days. So don't be shocked if this looks a little complicated. I just want to show what the different possibilities are and what we will be explaining throughout the next days. So CUDA.jl at the lowest level provides wrappers for libraries such as the CUDA driver, but also application libraries like cuBLAS, cuFFT, cuRAND, and all of the other ones that are provided by default as part of the CUDA toolkit. We also provide a compiler to generate PTX code, which is the virtual instruction set architecture that you need for programming NVIDIA GPUs. We have a sort of Julia dialect with some custom functionality that allows you to write Julia code that's compiled to kernels. And built on top of all of that, so built on top of the compiler and built on top of the libraries, we have array functionality that makes it simple and easy to use a GPU without actually having to write your own kernels. So I'll start by demonstrating that. I'll be implementing, as a quick introduction, the XPY operator, or A times X plus Y, which is one of the examples I'll be going back to a couple of times during this course. A simple native implementation that would run on the CPU would consist of writing a function expy bang. Bang is a Julia notation to say that we mutate one of the arguments, where we write in place broadcast that performs the element-wise multiplication of A with X and an element-wise addition with Y. So if we execute this on a bunch of CPU arrays, which I construct here using the bracket syntax, we get some answer. The easiest way to port this to the GPU is by just changing the CPU array type to a GPU array type called CuArray. CuArray is the basic type that you will be used to allocate and operate with GPU memory. So if we do this, we change X and Y to reside on the GPU. Alpha is a scalar, so that can remain a simple scalar. And the Z output, we use the similar function, which is a typical function that allows you to write generic code that's not tied to the CPU or to the GPU, but in this case just allocates a similar container. And as I'll show later, this is one of the generic functions that makes it possible to write fully device or accelerator agnostic code that can then be easily ported to run on a GPU by just changing the input types. So here I do that as well, and what we see, we get a output CuArray type with the same answers. So again, that's the easiest way to write GPU code, by just using array abstractions. But if we peel back one of the layers, for example, how this broadcast kernel is implemented behind the scenes, you might want to write a custom kernel, which I do here. I define XP kernel, which is using the, as I mentioned previously, the dialect, as I mentioned. For example, it calls the thread IDX function, which is a typical CUDA function that gives you the current thread index to work with, and it uses that to perform a scalar operation, and then we launch our kernel by calling the add_CUDA function. Executing this gives all of the answers we expect. However, a kernel like that is much too simple. There's various restrictions when using GPU devices. For example, Going back to my simple kernel, here I was launching a number of threads that corresponds to the length of my input array, which is not supported in that you can, on many GPUs, only launch 512 or 1024 threads at the same time. So you'll have to do something more fine-grained. For example, here I'm doing a very typical computation of my index by incorporating the block index and not only the thread index. Still works as expected. And even though this now seems like a lot of complexity where the casual broadcast implementation was very convenient, there are some reasons to using this already, because if we profile both implementation using the, this doesn't have to be here, using the built-in profiler in CUDA.jl, we will see that our custom kernel implementation uses fewer registers than the broadcast implementations, which may have some performance advantages. So the profiler ran, but as you can see, the output is a bit mumbled. This is because of a bug in JupiterHub, and this is why at the very top I should have a workaround. Oh, it's not here. Here, this is a workaround for the bug in Julia. So once you see the the profiler output wrapping around and being completely unreadable, just evaluate this output. And if we then evaluate again, now you can see that we get a scroll bar to easily scroll the profiler output, which can be a bit verbose. So again, I was going to profile both implementations. So this is the baseline our custom implementation. This is the original implementation, and we can see here that our custom implementation only uses 8 registers, while the broadcast implementation uses 32 registers. And finally, another way to use the compute XPy is by using the cuBLAS libraries. We can do this simply by calling cuBLAS.xp. But as you can see, this breaks. It breaks because we're using in64 array inputs, whereas the cuBLAS library only supports in32 and floating point inputs. And this shows what one of the disadvantages is of only building GPU language support on top of these libraries without having access to a compiler, namely that oftentimes you're using more complicated types that the library doesn't support. And for that, CUDA.jl has a compiler that allows you to write generic functionality that works on all kinds of inputs. But for this demonstration, let's switch to a float 32 input, and now you can see that the cuBLAS version will complete as expected. And we get the expected results once over. And let's benchmark this as well. Note that these timings that are being reported here can generally not be relied on because you're only executing the kernel once. It's going to be noisy, and generally, as I'll explain later, if you want to do robust benchmarking, you'll have to execute the code multiple times using, for example, benchmark tools or some of the other profilers that we have at our disposal. So now, before moving on to the next notebook, I'll have to kill this notebook. Now, strangely, the JupiterHub interface doesn't show me that I have a notebook empty, but on my desktop it did. But just for good reasons, we'll have to shut down our kernel, and then we can move on to the next notebook. Did anybody have any issues following along with executing the functionality from this notebook? Okay. Continuing with the first actual notebook, I'll first be explaining how you use the CuArray type to program a GPU. So I already mentioned very briefly the broadcast operation. But CuArray actually covers two use cases. On the one hand, it's a container for memory, for device memory, for unified memory. So it represents some memory that's accessible on the GPU. And on the other hand, it's a way to dispatch to functionality that's implemented using GPU kernels. If you call a broadcast operation on a CPU array, you'll be broadcasting on the CPU. If you call broadcast on a CuArray, you'll be broadcasting on the GPU. Crucially, though, this is an object that resides itself on the CPU. So CuArray, insofar as a CPU object with a pointer to GPU memory within. That's an important distinction that will come relevant later. So one way to construct a CuArray is, of course, by calling the CuArray constructor. Maybe let's jump a little back first. At the top of every notebook, I'll have this preamble, which again activates the current environment, makes sure that all packages are available, and then imports the CUDA package. I'm going to assume that this is always what you start with executing, so that CUDA and other relevant packages are available throughout the notebook. As we noted with somebody, this actually shouldn't be doing any pre-compilation because we pre-compiled everything as part of the first notebook, but apparently for some reason it seems to be pre-compiling over again. But even if it takes 2 minutes, the environment will be functional afterwards. So back to CuArray. Easiest way, or the one way to allocate one is using the CuArray constructor. But we also have a shorthand, which is the Cu function. And you'll see that being used a lot in this notebook on the internet, where you can just do Cu of some input, and it'll try its best to put that on a GPU. Cu differs from the CuArray constructor in two ways. On the one hand, it's smart and recursive. On the other hand, it's opinionated. Opinionated meaning that it'll change float 64 inputs to a float 32 because for many users, a float 64 is extremely slow if they're using consumer GPUs. On these clusters, of course, that's less of an issue. It's still twice as slow. But you can, I'll explain later or explain offline how you can still use the same functionality without that opinionated conversion. The other important feature of the Cu function is that it respects the object hierarchy. If you call the CuArray constructor on for example, a adjoint, you again get a plain CuArray containing float 64 numbers. However, the Cu function is recursive and it's going to try and do its best to retain the structures. For example, if I do Cu on an adjoint of a CPU array, you see we get a adjoint of a CuArray. Whereas if you call the CuArray constructor directly, you just get dense memory. That's an important distinction. It might matter if you don't want to materialize some memory. For example, if you have, I don't know, a diagonal matrix, you probably don't want to materialize that because it'll blow up in memory. You want to retain the structure, and then the Cu function is convenient. The goal of the CuArray object is to make it as convenient as possible to use the GPU. And to do that, we've implemented a whole bunch of functionality from the Julia standard library, from the Julia base standard library, and we've implemented that with GPU-specific functionality. In some cases, that means that we'll use cuBLAS. For example, if you do a matrix multiplication, A times A, we'll automatically use cuBLAS behind the scenes. But for other operations, for example, when you're doing a matrix multiplication of unsupported types, or when you're doing something that needs compile, like this broadcast expression, then we'll be using our JIT compiler, dynamically generates kernel code for you, cache that, of course, and execute it. But that's also why this first execution always takes a bit, because the initial compilation takes a while, but it also has to compile the compiler because of how Julia works. So that takes a while. Again, executing this a second time is just blazingly fast, but also executing this a third time with some additional functionality which necessitates new compilation will be fast as well because the compiler itself has been compiled. So again, the time to first plot, as we often call it, the time to first kernel with GPU code can be a little daunting, but it's improving, and once it's set up, it's fast. So that simple broadcast expression I showed that, A element-wise multiplication with A, it looks simple, but behind the scenes, this is syntactical sugar for Julia defining a new function, an element-wise operator, where it does element A times B, and then calling that using the broadcast function. And as you can see, that generates exactly the same result. There's some convenient syntax for that as well, using the do block, which can be useful if you're actually writing very complicated element-wise conversions, element-wise operators where the dot syntax is a bit verbose. But again, it's crucial to mention here that this generates a new function and will dynamically compile new kernel code for you. And you can peek behind the scenes by, for example, doing this add lower from the meta standard library, and it'll show you that it dynamically builds up a function that performs all of the operations and then flattens them using the materialize call. So this is an example of an abstraction that requires a JIT compiler to work. And we have a bunch of these. For example, map is also simple enough, just almost a synonym to broadcast, but it doesn't do the broadcasting behavior where the inputs have to have the same size when you use map. Whereas with broadcast, you can, for example, broadcast a number with a matrix, and it will automatically supposedly extend the dimension of the number to match that of the matrix. But another very important generic function, higher order function that we have is the reduction, which also is implemented by CUDA.jl using a parallel reduction. And again, it's important because we're convolving, as you want, a standard library definition of the reduce operator with whatever user-specified function you throw at it. So in that sense, we're combining both a standard library function and your user code together to generate new kernel code and execute that on the GPU. And this is one of the things that is a little harder in other languages where you don't have a compiler. You can, by default, reduce is going to reduce to a scalar. That requires the GPU to synchronize, because if you want a number out of a kernel, it actually has to wait until the computation finishes. Whereas if you tell it to reduce specific dimensions, it will reduce to an array. And as we'll note later, this is important because operations that return arrays can be executed asynchronously, meaning that the CPU doesn't have to wait until the GPU finishes, not until you actually copy back the array to CPU memory and access the value that it reduced to. The DIMS keyword can also make it possible to perform multiple reduction as once. For example, here I'm only reducing the first two dimensions, not the third one. So in that sense, this is going to be performing 3 reductions using a single kernel. And we also have a version of a reduction that maintains the interim sums, which will be relevant to one of Samuel's exercises. Question?
I did you benchmark the two, and the second one is much faster. Is that the reason?
Yes, but also because your benchmark is wrong. We'll get to that. So the question, maybe for the recording, was that the second version of the reduction was much faster, where we're reducing to an array. But that's because if you benchmark something, you actually need to synchronize the GPU in order to know how long the execution took. Now you're just benchmarking the time it takes to launch the operation. But we'll get to benchmarking in very short notice. CUDA.jl also has some, most of the time we use dispatch to select functionality that's GPU compatible for you. So if you do matrix multiplication or you call reduce, we know that one of the inputs is a CuArray. So that helps you helps the system select the GPU compatible implementation. For some functions, there is no CuArray input, so we need to have a CUDA specific version. For example, if you want to allocate ones or zeros, which are very common functions, you can just use CUDA.zeros, CUDA.ones. Same with the rand function, which is a random number generator, which again is built on top of CuRand for the types that CuRand supports, and is actually built on top of our own native random number generator when you want to generate random numbers for types that are not supported by CuRand. So this is some high-level functionality that introduces how to use the CuArray type. Before jumping into an exercise based on this, I also want to explain some common issues that you might be running into, or common pitfalls, if you want. The first one is that even though we have lots of functionality implemented, we don't have every array operation implemented. And as a result, we might be falling back to some functionality that's implemented in the Julia standard library. And sadly, many of those use for loops that, for example, in this case, compute a very simple sum by iterating over every element. Our compiler does not handle this because this is in essence just code executing on the CPU, and it will be fetching one element per time from the GPU and actually computing the sum on the GPU. And this is what we call scalar iteration, where some algorithm is going to iterate every element scalar by scalar and compute something. And this is, of course, not how you want to use a GPU. You're actually not using the GPU. You're just copying data from the GPU, copying it back afterwards. It does work, however. It does work because it's often convenient when porting CPU code to the GPU to at least allow this and make sure that some parts that you have ported already at least compute the correct things. So that's why we don't disallow this from the get-go, but we do print this nasty blob of warning. It's only going to be displayed once, so it's going to mention that this is horribly slow, don't do this, but if you really want to, be my guest. And the second time it's gone. Most of the time, however, if you write some production code, you want to disable scalar iteration because it's going to wreck performance, and that's when you can call CUDA.allow scalar false. And so if you do this, all of these kinds of scalar accesses are going to be completely disallowed. It's going to throw an error. And of course, again, there's cases where this doesn't make sense. For example, when you're using unified memory, this can be fast, but I'll get to that in a later notebook. So this is something you generally should do most of the time. However, at the same time, it can happen that you easily run into this, especially when using very complicated wrapped objects. If you show them in the REPL or you show them in a notebook, you might be triggering some display code that accesses element by element, which actually isn't too bad. So for example, here we have an adjoint of a CuArray, and the show functionality still works fine because we have implemented all of the show functionality for one level wrapped arrays. But if you wrap that again, for example, here I'm creating a view of this adjoint of a CuArray, the show functionality will actually trip up the scalar iteration warning. Nowadays, this is better in the REPL because we can discern between code that's doing display and code that's doing computation, but in JuliaHub, we don't do this yet. So just saying, you might run into this if you always disable scalar iteration, but it can be a bad situation. It can be okay. Sometimes, of course, accessing a single value is just okay. For example, if you're doing this kind of reduction to an array, afterwards you of course need to fetch the value, and for that we have this add allow scalar macro, which you can just wrap any code with to allow scalar iteration temporarily, which in this case is completely fine, and we use this in the CUDA standard library for many of these operations that reduce to a scalar. Lastly, another issue you can run into when using CuArrays is that the CUDA standard library might try to use a CPU library like the CPU BLAS implementation or the CPU LA-pack implementation. It shouldn't. And most of the time this is a bug because the Julia standard library should not use CPU libraries for arbitrary inputs, but it can happen. And for example, here I'm mimicking what would happen behind the scenes where we're actually doing a C call to a C library, whatever, doesn't matter. And as part of that C call, it wants to convert a CuArray to a CPU pointer. And we also disallow that. There's no way this can work. Again, unless you're using unified memory, but I'll be getting to that in a future notebook. So with that, I think I have covered the basics of the CuArray type and the basics of the issues you might be running into. So let's try and do a small exercise. There we go. Let's try to compute the root mean square error of 2 matrix inputs on the CPU, on the GPU, and then later we'll do this with a custom kernel. But for now, let's try to stick implementing this for the CPU and then executing this on the GPU. So let's show the implementation I came up with here. It's, of course, very simple, but if you're new to Julia, it's getting familiar with the way you express things here. So I've defined a root mean square error function taking 2 inputs where we compute the difference, then use a broadcast kernel to compute the power of 2. And finally, we take the sum, we divide it by the length, and we take the square root. And this is the CPU implementation, and to quote-unquote port this to the GPU, we use CuArray inputs, and that's it. We get the same answer, in this case exactly the same answer. In some cases it's not going to be exactly the same because, for example, the way the sum is executed in parallel doesn't give you the same guarantee that elements are processed one by one as if they were serially. So because of how IEEE floating point works, you can get quite some differences on the precision of answers. Benchmarking this is easy when we use the benchmark tools package, which is something I'm going to delve into deeper in the next notebook. So let's just demonstrate it quickly here. You see by the star that it's still loading. The CPU implementation for 2 inputs of 1024 by 1024 double precision floating point inputs took 3 milliseconds, and on the GPU it takes 145 microseconds. So that's of course a very impressive speed up, but at the same time it's a bit of a lie as well, because we're not including the time it takes to send this data to the GPU, which is a common fallacy when comparing, when showing off how quick a GPU can be if you're not including the data transfer time. On the other hand, for many applications, the data transfer time doesn't matter because you slot in lots of memory and then you do lots of computations. So you amortize the cost of data communication. But it depends on your application. Here, though, we're showing that the GPU with its massive parallelism can do can speed up your implementations a lot. In the next notebook, I'll be demonstrating how you actually properly benchmark this. So let's shut down my kernel, open up the third one, clear the output. And again, anytime I'm using the CUDA.jl integrated profiler, I'll be adding this HTML workaround cell to the top of the notebook, which you can just evaluate and should result in slightly less manageable output. So I'm going to be showing the different ways you measure execution time on the GPU. If you're somewhat familiar with Julia on the CPU, you might simply do something like this, where you generate some inputs, you perform a warm-up, because of, again, Julia is a JIT-compiled language, so the initial invocation takes a while, and then you stick the @time macro in front of an arbitrary expression to compute or to visualize how long it took. And here we get a result that seems much, much too fast. And that's because, as I've briefly mentioned already, GPUs execute asynchronously. So every operation you send to the GPU from the CPU is going to start executing on the GPU, but the CPU is not going to wait. You actually have to manually, explicitly ask the CPU to wait for the GPU in order to be able to safely inspect the results that have been computed. And in Julia, we do that most of the time for you. For example, when you copy a CuArray back to the CPU, or you just inspect results, we are going to implicitly synchronize, because otherwise there's no safe way to use that memory on the CPU. However, when doing time measurement, it's important to do the synchronization yourself, unless, of course, you're including a memory copy or you're, say, reducing to a scalar, in which case you always have to synchronize anyway. You can simply synchronize the GPU by calling the synchronize function, which is a function that's defined by CUDA.jl. So first we synchronize beforehand in order to make sure that the GPU is fully idle. Otherwise, our benchmark might include the time of previous computations. And then we time both the submission of the operation and how long it takes for the GPU to become idle again, and in other words, to complete the operation. So if you do that, we get a much more reasonable result. It's actually a bit too slow, and that's because of the presumably initial compilation of the synchronize function, for example. It's somewhat more convenient to wrap your function in the add_sync macro, which is nothing more than just evaluating your code and calling synchronize. However, this still returns your original computation, which might be a little more convenient if you want to put this in an application. Otherwise, you have to first assign your result to a variable, then synchronize, and then you can use that variable. With the add_sync macro, we do that for you. And finally, with the add_time macro, we've specialized in CUDA.jl. We do all of that for you. So basically, most of the time you do add_time with a GPU application or a CUDA application, you just have to do CUDA.add_time. And in addition to the time spent executing, we will also report the number of GPU allocations and how long we spend managing memory. So here, for example, you can see one GPU application, and that's the result of the A times B that we have to allocate and store the result into. If for some reason you need to access these timings in your application, for example, to track metrics or so on, you can use the add_timed macro, which will instead return all of the internal, both the value as well as all of the details on, for example, how many allocations there were, how many bytes were allocated, and so on and so forth. So this can be interesting for keeping track of well, application performance. And finally, we also have an equivalent of the add_elapsed macro, which is also a very commonly used macro in Julia on the CPU, which returns the number of seconds an operation took. And here we also have that on the GPU, returning the time it took on the GPU to execute this operation. And this actually uses, for people familiar with CUDA, this uses CUEvents. So it submits an event, submits the operation, submits another event, and then it computes and subtracts the execution time between two CUDA events. Of course, most of the time, if you're actually benchmarking, you have to use a more robust benchmark. You cannot do a single measurement most of the time. And for that, benchmark tools is the go-to package in Julia. It does some statistical analysis, it does some attempts at doing a much more robust benchmark. Of course, the same issues of synchronization arise, so we have to always, most of the time, wrap your GPU expression in an add_sync block before passing it to benchmark tools. You also get some nice visualization. So here we can see 339 microseconds, the standard deviation, and a little plot. Note that this memory estimate, again, is a CPU memory estimate, because benchmark tools knows nothing about the GPU. If you need to know about GPU allocations, use CUDA.add_timed. Again, the same issues that we have with benchmarking, we have with profiling. So if you look at the Julia documentation about how to profile code, they'll point you to the add profile package and the add profile macro. So let's do this. I'm adding this noise floor argument here to hide most of the output, because then the output is manageable. And we can see here that there's nothing GPU related in there, except for the fact that we're most of the time spending in our synchronization functionality, which makes sense because we're profiling the CPU here, and the CPU is just waiting for the GPU to finish computing, which is the call to the synchronize function. And that's why we have implemented our own profiler in the CUDA package built on top of NVIDIA's CUPT library, which is the same functionality that's being used by NVIDIA's profilers, which I'll get to later. So with the add profile function, which I've shown you already, we get a fairly pleasant overview of everything that happened on the GPU, summarized across the amount of times that every operation was called. So that's the column calls here. Everything is summarized, and when there's more than one invocation, we get a time distribution about the performance of this specific operation. We also highlight, respectively, in red and in bold, the operations that took the longest. I think it's 90th quantile, 90 percentile, and 75th. And we split the activity view in what happened on the CPU, that's relevant to the GPU, and what actually happened on the device. Lots of information. The first thing you should probably look at is this number, and that tells you how much the CPU was actually active during our profiling trace. So here we ran for 10 microseconds. Maybe let's actually run again in case there was some, yeah, that's slightly better. Again, profiling, compilation overhead. The first time we invoke the profiler has to be compiled. So in Julia, it's always better to invoke things twice. So here we can see that we were active 70% of the trace, which is okay most of the time. If your application saturates the GPU for 75+% of the time, for small applications, that's fine. For larger applications, you obviously expect higher numbers. But this gives you a very good initial overview of how efficiently your application was using the GPU, at least with respect to the ability to submit sufficient work. It's still possible that the work you submitted is badly implemented, but in this case, at least, the GPU is doing something 70% of the time, which is fine. And you can see here that the time just to launch our kernel took 20 microseconds, which is fairly significant if you compare that to the time it takes the CPU to perform certain operations, like, for example, a small matrix multiplication. And this also shows that using the GPU only makes sense if your problem is large enough, because otherwise you'll just be hitting into the launch time overheads, especially if your operation involves multiple kernels. If you want to do some more robust profiling, you can use @bprofile, which is going to be running your application for 1 second. This is customizable using arguments to @bprofile. You should look at the documentation for more details on that. But so here we just have a small harness that takes care of warming up. So it invokes your application once, and then it invokes it all the time for 1 second, making sure to synchronize every operation. This gives you some additional, especially time distributions that can be interesting. For example, here we have the benchmark harness introduces what's called an MVTX range, which encompasses a single iteration. That's why it's called bprofile with iteration. And here you can then exactly see how long one iteration took and what the statistical distribution of that was. And this output should be fairly similar to just using @benchmark with CUDA.add_sync, because benchmark tools is doing something similar. It's measuring from the CPU. But it gives you a bunch of additional information on how long it took to perform certain API calls and so on. And finally, if you're, instead of wanting a summarized overview, want to see something that more resembles a timeline, you can pass trace equals to true. And this will just give you the start time of every event and not aggregate them, which can be useful to gather some additional details on bubbles when the GPU is not doing anything. But it also gives you additional details on every invocation. So when we aggregate kernel invocations, we cannot display information about the kernel invocation itself. But if you trace it, we can, for example, tell you how much memory, how much registers this kernel used, how much shared memory was used, what the throughput of memory operations was. So this can also be useful to figure out some more details on slow GPU operations. So this was the implementation that we came up with. Let's try profiling this using @bprofile. Now this is the output, and it highlights a couple of things. For example, the amount of kernels that we're launching. Now, depending on what implementation you came up with, it's possible to have more or fewer kernel invocations. But I would propose trying out the profiler functionality that I've shown based on the simple implementation that I have here, and try to optimize it, for example, by reducing the number of kernel launches that are present. So I propose we do this and then maybe go to lunch afterwards. Give people some time to try out the profiler tools and slightly optimize the implementation. Is that okay? -b was a separate invocation of a kernel. That's the GM kernel you see in the output here. It's have to know that this matches the A-B, of course, but this is a specific kernel in cuBLAS. Then we have the broadcast for the power of 2, and then we have the reduction, which requires 2 kernels. So that's a lot of kernels, and a lot of kernels generally isn't great, because, for example, here we have to first allocate the output of the A-B. Then we have to allocate the output of the reduction of the broadcast, and then only then we can reduce in 2 steps. And the reason this is suboptimal is, 1, launching kernels takes a while. 2, because we have to allocate temporaries. That means the GPU has to write to global memory multiple times, which is slow. So let's try to avoid these. And the simplest way initially of getting rid of the A-B is by folding it inside of the broadcast by doing an element-wise A-B. So the original execution time was 430 microseconds of an entire iteration. By folding it in there, we dropped to 360. And as you can see, the GM kernel is gone. And this is generally as far as you go, but I want to show that it's possible to fold operations together some more by, for example, in this case, folding the broadcast inside of the reduction. And the key insight here is that a broadcasted object is something in Julia that behaves as an array. So we can create a unmaterialized broadcast, which is an object that represents the element-wise operation we want to do and on which inputs we do so, but it doesn't eagerly compute it. And because this behaves like an array, we can actually pass it to other array operations, like, for example, the sum. And this, as you can see, is unexported functionality. So in that sense, it's slightly advanced, but there's packages that make this much easier. For example, there's lazyarrays.jl, which exposes a single macro. I think it's @-, and you can put that in front of arbitrary Julia code. And it will look at the code and it will try to make as much lazy as possible. And for example, if you put it in front of the broadcast, it will automatically give you a broadcasted object instead. However, it should also be noted that not all array operations support arbitrary array inputs like broadcasted. For example, some here does, but others might break. Anyway, in this case, it works. So let's look at the performance, and it dropped further to 213 microseconds from originally 430, I think it was. So that's a significant reduction by just getting rid of kernels as much as possible. Again, because getting rid of kernels makes it possible to avoid temporaries, for the compiler to do better optimization, and to avoid global memory writes. So it's an improvement on many levels, and as such, it's also something you should always look at first when writing array operations. However, if we want to go beyond this, then we have to use some external profilers. So I mentioned before that you can use CUDA's integrated add profile with trace equals true, which gives you a textual timeline of operations, but of course that's not really pleasant to look at. NVIDIA's profilers give you visual tools that give you, for example, a visual timeline. In fact, they have multiple tools. It's all part of the Nsight suite. And they recommend, as do I, that you always start with Nsight Systems. Nsight Systems is the application that gives you application-level profiling information. It helps you to find so-called bubbles when the GPU is not being saturated, it's not active, but it also helps you profile an application as a whole because it gives you a CPU and a device timeline, so you can neatly correlate what you do in a CPU when that happens with when something happens on the GPU, and you can figure out, am I synchronizing too much or not, should I spawn off work in parallel, and so on and so forth. Only when in the timeline you spot a kernel that's extremely slow, you can go to Nsight Compute, which is the application that gives you all the kernel level details. For example, which instruction is slow, when are you stalling memory, which type of memory transfers are happening, and could they be optimized or not. There's also Nsight Graphics, which is the equivalent for graphics applications, but we're not dealing with that. In order to invoke such a profiler, you have to run Julia under the profiler. So it's slightly more involved, also because you have to install software for this. You have to install Nsight System, both on the systems where you profile to run Julia under, but then also on your laptop or on your host desktop to visualize the traces that Nsight generated. From the CUDA side, it's pretty simple. You just have to invoke CUDA add profile with external equals true, which tells CUDA.jl not to run the integrated profiler, but instead activate the external profiler. So let's start with Nsight Systems, because at this point in the notebook, we're still working with application level optimization. We're not writing our own kernels yet, so Nsight Compute is not interesting. Nsight Systems can run in two ways. You can have it profile the entire application, or you can have it launch, run an application, and only profile when the application requests so. And this is why you use CUDA.add profile with external equals true. You only tell it to profile a very small subsection of the application where you're doing your actual GPU operations. And this also makes it possible to use Nsight interactively. So you can spawn Julia under Nsight, and then you get an interactive REPL, and you do all of your work. You can even do so with Jupyter. And as soon as you mark some code with CUDA.add profile, Nsight will activate, will profile your code, will write a file to disk, and then you can open this file. And this is the workflow we're going to be using. It's possible to have Nsight actually connect to a remote system and visualize everything automatically. But with how the cluster is set up, that's slightly contrived, because then you need to have SSH access to be able to SSH into the jump host in order to SSH into the compute node. So that's fairly tricky. So instead, to make this somewhat more manageable, I have provided a script. It's called Julia_Nsys, and it's part of the course directory. And if you execute that script, we will automatically launch Nsight systems, as I have deployed on the cluster in a directory of mine on the Scratch space. It will start Julia under Nsight, activated in the environment of the course directory, so where all of the packages have been installed and are pre-compiled. You also, however, have to download Nsight system. So the download link there is clickable. If you click on it, you go to the NVIDIA webpage, where you might have to make a developer account, but then you can just click and download Nsight systems. It comes with a run file, which you can just execute. It doesn't require root permissions. It will just extract in the folder of your choice, and within that you will find the Nsys UI binary you can execute. If you're on a Debian system, you can use just a .deb or .rpm. For Mac OS, there's also a full-fledged client, so even though Mac OS doesn't support CUDA, you can install Nsight systems to visualize traces on your Mac. And for Windows, all the same. So I would propose to, what time is it? 47. Oh, we actually should go to lunch, I guess.
You said if we bought it to 1 and 1.
To download Nsight systems and to try and get this working on your system together with the Julia Nsys script we have on the cluster. So you should just open a new terminal, go to the place where you have checked out, and there you run Julia Nsys, and as you can see, it will automatically launch under Nsight system in the correct environment, and you get a REPL. And in there, you can then execute these instructions. Let me actually just fully demonstrate it for you. So again, I have to shut down my notebook first, because we only can have one active session. In my REPL, I can now import CUDA. And once that's done, I can do CUDA.add profile. Let me first warm up. Some simple GPU operation, which again takes a bit to compile. And now we can put CUDA.add profile external equals true in front of that. As you can see, this activates Nsight automatically. And this generates a report. Crucially, that report will be written into a Scratch folder that my script created in your home directory. See this folder? If you double click on it, we'll have our report that has been created seconds ago. I can download this report. And there it is. I can then open Nsight systems, and here I can open my report. And there we go. If we zoom in on what seems to be the relevant bits, which is of course trivial, we get our kernel invocation. There we go. Firefox. I'll leave this visual which represents all of the relevant bits. I propose we try and get this set up before lunch so that we can then use Nsight systems after lunch when we focus on optimizing a batched version of the root mean square error implementation. I'll give a quick run down of the NVIDIA Nsight systems user interface because it's a fairly complex interface that may seem daunting to people who aren't familiar with it. So here I've opened the report for the simple broadcast operation that I demonstrated as a smoke test. You can see a couple, so essentially it's essentially it's a timeline of what happened during the tracing of the CUDA.add profile code. You have a bunch of possible timelines here to inspect. For example, the CUDA API one is an interesting one because, as you'll see, the API calls that get executed are visible there, but of course not much is visible here because it's so zoomed out. The easiest way to zoom in is first have a look where the operations of interest happen, and this is around here, and then right-click, zoom into selection. Let's do this another time. This, of course, is tiny because I'm not executing much on the GPU. There we go. So let's zoom in a little more. Zoom in to selection. Right. So this would be the default view that you can see. And as I mentioned, here you can see all of the API calls that the CPU executed. So the CPU requested CUDA to do something, either to launch a kernel or to copy memory and so on and so forth. If you hover on it, you can see some additional information. For example, there is where we started the profiler. Here, the red boxes are typically memory operations. So here you can see where we allocated some memory from the memory pool. We copied some memory into that because we did so the operation was CuArray of the array containing 1 and add another 1 to it. And then finally, here you can see the broadcast kernel that got executed. Well, actually not executed. This is where the CPU requested the broadcast kernel to execute. If you expand the timeline from the CUDA hardware, we can actually see some details of the actual kernel being executed. The blue at the top is just an indication of the GPU usage. If we actually have a look at what was executing at the kernel trace, we can see the actual kernel invocation, the kernel execution, which here was a broadcast kernel, along with some interesting details about the execution. So these are things you could also see with CUDA.add profile and the trace equals true argument. For example, what was the exact launch configuration, how many registers were used, and so on and so forth. Essentially, this shows that for such a simple operation, which basically starts here, we're spending an awful lot of time for the GPU only to be active for a couple of microseconds. So instead, let's try and do this on a more realistic example, being our root mean square error function. So I replicated everything here in the notebook as well, because it may be tricky to set this up. And again, if you're using this locally, you may be interested in running Nsight from within Jupyter, because then you can just quickly switch between the Julia REPL and the REPL running under Nsight by switching the active kernel. Because I quit my kernel, I'll have to re-import CUDA.jl. So let's do this. And while this is running, I can go down. So we can now profile what? Did this not activate? Apparently not. So now we can profile both our implementations, and I'm going to show the profile results of our so-called slow implementation, where we used multiple kernels because we didn't fuse the operations together. And here you can clearly see that we have multiple kernels being active on the GPU. The first launch taking a long time is something I'll come back to. And for the fast implementation, you can see that there's only a single blob of GPU activity. It's still 2 kernels, but that's because of how our MapReduce implementation works. So this mistake shows that I actually have multiple Julia notebooks active, and this is probably, yeah, there we go. That's the one that's still active. And this is because the cluster is running in so-called compute exclusivity mode, which means that every GPU can only have a single process attached to it, which can be convenient if you don't want to accidentally use a GPU that's doing other computations. But for interactive sessions like this, it's a bit of an annoyance, of course. So here I showed that we can hover the kernel and get some details. And one interesting additional library to use with the profiler is the NVTX or NVIDIA Tools Extensions library. Because this library allows us to add additional information to the timeline and will be visualized in the trace. For example, after importing NVTX, which is a separate package, we can do nvtx.add_range with a string. And then an additional timeline in NVIDIA Nsight will show you the duration of this range. Once again, though, this now apparently takes 10 milliseconds, which is absurd given the timings that we were dealing with. And this is the same issue as what I mentioned before, that the initial kernel or sometimes initial API call can take an awful lot of time because of the profiler, the CUDA profiler, getting initialized. So it's always recommended when you profile code to profile your code twice. And it's convenient to just put it in an NVTX range, so you can clearly and easily zoom in on the one range that matters. For example, here I'm zooming in on the second range, and as you can see, it only takes 96 microseconds, which is much closer to what we were expecting. A more convenient way of using NVTX to annotate information is to just do nvtx.add_annotate attached to a function definition. And this will automatically encapsulate the body of this function with an NVTX range. And as such, you'll be able to spot the function as invoked in the NVTX trace. And this is especially convenient when you have a large application and it's not clear where the slowdown is, to just open Revise, which is a tool that allows you to automatically pick up changes to your source code, and then just in your editor add CUDA nvtx.add_annotate to a bunch of functions where you suspect that they may be slow. And as a result, you then see in the trace the timings of exactly those function invocations. And that's a very convenient way to easily drill down to those Julia functions that are problematic in your applications or that need to be optimized. And these traces are also visible in the integrated profiler. However, it's a little more convenient and a little more pleasant to see it in the trace because they can also be nested. And it can get a lot quite quickly. So our root mean square error implementation was already fairly optimized. And a more realistic setting may be if we want to compute the root mean square error of a bunch of inputs. So let's try and generalize our implementation, where it now takes an additional n batching dimension. So here I want to compute n times the root mean square error of these 16 inputs.
Just maybe a bit on before what you said, but we use 2 kernels in the more advanced version. Can we go down to 1, or it's the minimum?
You mean the fact that the MapReduce kernel still uses 2 kernels? So the question was, for the recording, whether it's possible to optimize away the fact that the some kernel internally still uses 2 kernel invocations. The reason we do that is somewhat involved, namely, when we're reducing values to a single scalar, we're trying to use the GPU as efficiently as possible, and for doing that, we're using all of the multiprocessors in the GPU. However, those multiprocessors, which coincide with the block hierarchy we'll be seeing next in the kernel programming notebook, they cannot be synchronized between them. And as a result, it's unsafe to synchronize values into a single global memory location, because otherwise the blocks may override values. One solution there is to use atomics. We're not doing that because atomics are generally limited to what types you can use. So as a result, we're first reducing to a partial array that contains one value for every block, and then we're doing a second stage reduction. Generally, this shouldn't be too costly because we assume that the initial MapReduce invocation will be very costly, so the launch time of the second kernel will be hidden entirely by the execution time of the first. If you want to avoid this, we'd have to change the MapReduce implementation to use atomics, which is some feature we could add if this is problematic. In the next notebook, we will be developing a partial reduction that uses atomics, so that will only use a single kernel invocation. So as an exercise of the profiler, let's now try and take your root mean square error function and apply it n times for this third dimension of these inputs. And initially, it's simple enough to just, or at least that's the goal of what I'm going to demonstrate, simple enough to do so in a loop. So you just have a loop from I from 1 to n, and you want to execute your root mean square error function n times. Try to develop that, try to run that on the profiler, and try to see whether that behaves as you expected, whether the GPU is saturated, or whether there's improvements to be made in how this root mean square error function is being called n times in a for loop. So assuming that all of you have had some time to play with the profiler, I'm going to move on and show the optimizations I implemented to squeeze some additional time out of this batched implementation. So the initial naive approach might be, actually let's follow along and actually execute this so that we see some benchmark results, would be to take our fast implementation and then run it in a loop where we always take some memory where it should be applied to. So this is a Julia syntax. The colon is the Julia syntax of taking an entire dimension. So if you benchmark this, we get 9 milliseconds, which is respectable, but nonetheless, let's run it on the profiler. And we can see here that these are the kind of bubbles I was talking about earlier. So the GPU is not being active at that point, and this is generally something you want to avoid because here you're either not being able to saturate the GPU sufficiently, like not being able to queue up sufficient work, or you have a redundant too many synchronizations happening within your applications, making the CPU wait for the GPU to finish. So that's not the case here. So let's zoom in into a single iteration. And what we can see here is that outside of our actual iteration, we're first launching some get-index kernels that contain allocations or that require allocations to materialize values into. And these are part of the explanation why there's a bubble here. Those happen because of the slicing that we did in our implementation. This actually allocates a new output container. It's not a view, it's a slice that afterwards you can safely modify, and that's just the semantics of how slicing in Julia work. So the solution to that is to take a view instead by calling the view function on an input and then just passing our indices along, including the colon to specify that we want the entire dimension. We get a view which will represent a chunk of memory without having to take a copy. And this is safe here because we're doing a read-only operation on the inputs. It would, of course, be unsafe if we're mutating the inputs. There is a macro that makes this much more convenient, and that's the add views macro. If you just add views in front of any expression that does array slicing, it will convert those copying slices into views. And this again is something similar to, for example, the lazy arrays macro, which I mentioned before for making the broadcast lazy. It's a macro that you stick in front of an expression and it will mutate the expression to change the semantics. So let's benchmark this. Originally we had 9 milliseconds. The new implementation without the copies takes a long time to compile, 2.8 milliseconds. So this is a drastic difference, just avoiding the copies. If we have a look at the profile, we can see that the bubbles, at least from the CPU side, are gone, but there's still some bubbles on the GPU side. So we'll do our best to optimize those some more. One of the issues here is that, as I mentioned, we're reducing to a scalar, which basically requires us to wait for the GPU to finish computing at every iteration, which in this batched implementation is not ideal, because we don't actually care about the scalar result at the end of every iteration. We only want the results at the end of our batched computation. So instead, let's avoid synchronization by reducing to a pre-allocated vector. Now we can already see in the profile trace so here one of the modifications was that we now have to specify the dimensions, because specifying the dimensions makes it reduce to an array, and then we assign this array into an array of arrays, and finally we concatenate all of the results at the end of the iteration. The improvement isn't that drastic, but at least we can now clearly see that all of the memory operations are grouped at the end, and we don't have to wait anymore at the end of every iteration, which results in the iterations being back together a little more tightly. But if we were to zoom in, there's still some allocations happening at the beginning. And that's because we're still allocating our output container at every iteration. The final optimization is pre-allocating our outputs, which is also generally something that you should try and do with realistic applications. Don't try to allocate memory during, especially not the hot part of application. Try to pre-allocate as much memory as possible and write your functions in a way that they are mutating. So here I renamed my function to root mean square error bang. Again, the bang illustrating that we will be modifying one of the inputs, and we will be modifying the C input, which contains all of the outputs. And for that, I'm also taking a slice here of my output array, and I'm reshaping it in a way that the dimensions are compatible with my implementations. This is essentially making a 1-by-1 matrix out of a memory location. With just an implementation detail to make my implementation slightly more convenient. That's did I not? So now if we look at the profile trace, instead of having to do many copies at the end, one for every scalar result, we now have a single memory copy, and we also got rid of some more memory allocations that are happening at the beginning of every iteration. I'm not sure why this isn't executing, but I'm not going to look into this right now because I have my screenshots here. And finally, it's possible to fuse everything together in a single invocation of our root mean square error function. If we do so, for example, here, the way I did this is just by playing some more with the dimension inputs. However, if you evaluate this locally, you would see, well, my benchmark doesn't work. Let me try again. You would actually notice that performance degrades. In this case, that's also important to always benchmark your kernels, is that if you're fusing lots and lots and lots of kernels together, at some point you may come at the point that just the complexity, the sheer complexity of the kernels is going to increase the register usage too much, such that the occupancy, which is the amount of threads that can be active at the same time, degrades and performance degrades as well. So here we actually had an implementation of 2.5 milliseconds before. After fusing everything together, we regressed to 3.5 milliseconds. Even though on the profiler, this now nicely looks like a single invocation of a kernel, performance has degraded. And this is just to illustrate that when developing these kind of operations or applications, you should always try and benchmark at every point of development, such that you're not, for example, in this case, fusing too much together in a way that makes your kernel too complicated. So in summary, when you're developing a GPU application that's built on array operations, but also in general, try to fuse operations, because it helps avoid temporary allocations, but also accesses of global memory where the temporaries are stored. Avoid synchronization when it's not necessary in order to reduce bubbles on the GPU, and also try to bundle memory operations as much as possible. That means pre-allocating at the beginning, and only fetching results once at the end. And for those, you can use a bunch of tools. You can use the addTime macro from the CUDA package, or the addElapsed macro if you need the timings yourself. For interactive profiling, always use benchmark tools with addSync, such that you're definitely measuring the execution time of your kernels. For high-level insights, use CUDA.headProfile, and especially look at the amount of time that the GPU was active. And for more fine-grained application analysis, use Nsight systems. And finally, I also want to mention that if we implement array operations like this, despite there being a couple of GPU-specific things in there, like the mvtx.range, most of the operations here are fully generic. If we use functions like similar to allocate output containers, and otherwise don't hard-code uses of CUDA-specific functionality, all of this will still work on the GPU. Whereas if you specifically call into, for example, cuBLAS, or use all other GPU-specific functionality, you'll have to maintain multiple versions of your applications to be both CPU and GPU compatible. So it is possible and convenient to write your applications in such a way that are compatible with a wide variety of accelerators. For example, this would also equally well run on an Apple accelerator or on an Intel GPU, just by switching the input types. And that's just to demonstrate that we actually compute the values we want, and just for fun, let's also benchmark how slow the CPU is. The GPU implementation was 2.5 milliseconds. This is 150 milliseconds. So quite a significant performance improvement. If we want to go beyond these array operations, we'll have to start writing our own kernels, and that's what the following notebook is about. So I'm going to shut down this kernel and move on to the kernel programming. So again, before activating this, get rid of the package.instantiate.
We get the result final notebook.
It's already there. It's just on a different branch. And all of the results are also committed. So not only the exercises, but I meant the output. So in case that you have some, you can just look at it in GitHub and it'll show all the benchmarks and so on. So the next topic is on kernel programming, when we want to move beyond just using array operations, but want to define our own array operations or do more fine-grained uses of the GPU. So when you write a kernel, you're going to be writing a scalar function. And that is a function that executes typically for one value that you want to process, and it runs on one thread. So instead of using vectorized operations that, for example, compute a sum or do a broadcast, you will now write the function that computes the output for a single value. This kernel function is going to be executed massively in parallel on the GPU, and the GPU isn't just a bunch of threads, it's actually a bunch of shader multiprocessors which execute a couple of threads grouped in warps. So here you can see what we typically call a grid is executing on the device. What we typically call a block, which is a group of threads, will be executing on one streaming multiprocessor. And then within that, within the block, we have a bunch of warps. Those are groups of 32 threads. Those execute in lockstep, meaning they literally execute at the same time. This distinction is important because at every level we have different means of communication. For example, threads that run concurrently as part of a warp can just send a value from one thread to another thread by writing in a different register, because they're literally executing at the same time. You can safely write in one register and the other thread can then read from that register. This is an efficient way of communicating between threads running in a warp. At the block level, the threads are not running at the same time, but they're running on a single multiprocessor. And on that multiprocessor, we have a block of dedicated shared memory, meaning that threads running within the same block can use that shared memory to communicate with one another. And finally, at the device level, there's no specific means of communication. So if you want arbitrary threads to communicate with one another, you'll have to be using global device memory to write values to and to read values from. And those distinctions are crucial to making GPU implementations perform well. If you're always writing to global memory and reading from global memory, your GPU kernel will be slow. So before that, I'm going to briefly explain the syntax and the language features that we have at our disposal within a kernel function or for using and launching kernel functions. For example, if you want to define a kernel function, it's generally as easy as, I didn't import my package, did I? It's generally as easy as just defining an arbitrary function. It doesn't have to be annotated in any way. It's just a plain Julia function, and launching that Julia function by using the add CUDA macro. Again, the add CUDA macro supports a wide variety of keyword arguments. I'll be showing some. If you're interested in more, have a look at the docstrings by creating in a cell question mark and then add CUDA. Then you'll see the documentation of the add CUDA macro. You can pass arguments to kernel functions as long as they are bits types, which is Julia's equivalent to, for example, plain old data types in C. Just simple memory that doesn't contain any pointers, but just contains a value. For example, a string is not a bits type. So if we, again, clear output, if we want to invoke a kernel function and pass a string, we'll get a nasty compilation error which mentions that our string argument is a non-bits type. And it'll show which argument that is, even if it's a nested argument, because you could be using a wrapper container that is or can be a bits type, but only the contained value is not a bits type. And it will actually show the hierarchy of that argument, which argument is the problematic one. Not sure why. Clear all output, that's it. Okay. For some arguments, we do special things. For example, a CuArray is not a bits type because it's a complicated CPU object with not only a pointer to GPU memory, but also lots of information, some garbage collector information, and so on. So CuDevice itself is not a bits object, so wouldn't be GPU compatible. However, at the point of passing it to kernel, we are going to convert it to a CuDevice array, in this case a CuDevice vector, which is a bits type. Conversions like that are customizable. So if, for example, you're writing an application which has a very complicated CPU object representing something that you don't all need on a GPU, you can write a device counterpart of that type and register that with the system such that it will automatically get converted from one type to another type at the point of invoking a kernel. That's using adapt, the adapt.jl package. If you have more questions about that, feel free to ask. So as I mentioned, the CUDA macro has many arguments, and one of the most important ones is the threads equal something argument, which tells the driver how many instances of this kernel function need to be launched. So for example, here I allocate an array with 10 values, so I want to launch 10 copies of this kernel, which is going to modify one element of that array. So within that kernel definition, we have to use the thread IDX function to differentiate what this instance of this scalar function is going to be computing, because otherwise every instance of your function would be doing the same. So with this thread IDX function, we can query which is our current thread number, and we can use that to, again, differentiate what we are computing. For example, in this case, I'm launching 10 threads, so the thread IDX function will return 1 to 10 based on which thread is currently running.
Thread index is within a block, yeah?
Yes. Yes, it's not a global thread index, it's a thread index within a block. So I mentioned briefly in the introduction that we cannot just launch an arbitrary number of threads. That's because there's execution limits of how many threads of a kernel fit concurrently within a single streaming multiprocessor. And on this device is 1024. So if you want to use more than 1024 threads, for example, because we have more elements to process, you can subdivide by launching a number of blocks. For example, here I'm going to launching 5 threads using 2 blocks, which is 10 threads in total. And for that, we use a slightly more complicated indexing calculation, where we multiply our current block index, which is 1-based, everything in Julia is 1-based. We multiply that by the size of the block, and then we add the thread index. And as a result, again, I is going to go from 1 to 10, which is what we want in this case. And just to show how this works, within our array, I'm going to save a tuple of the thread and the block index. And if we execute this, we can see where we got 10 threads and their thread and block number for each of those threads. You can see the thread number goes from 1 to 5, the block number goes from 1 to 2. But this is not just a way of extending the amount of threads, it's also semantically meaningful in that threads on one block are going to be executing on one streaming multiprocessor. The threads on the other block are going to be executing on a different streaming multiprocessor. Generally though, it's good to rely on the CUDA APIs to determine how many threads and blocks to launch. So if you define a kernel function as we did before, we can pass launch equals false to CUDA. And this gives us a callable object, a callable kernel object, which we can also use for introspection. So here I'm asking CUDA by using the launch configuration function, which is defined by CUDA.jl, what the optimal number of threads and blocks is. So I add a show in advance in order to show it in the output. So here we can see that our config object is a named tuple containing a number of blocks and a number of threads. The number of threads here is CUDA telling us how many threads at most we can execute of this kernel. So I mentioned before that there's a device limit, only 1024 threads at most. However, there's also a kernel-specific limit, because if our kernel is using lots and lots and lots of registers, we cannot run 1024 instances of that function at the same time on a single streaming multiprocessor. And that's because the number of registers we have at our disposal within a single processor is limited. And this is also why, as we'll see in the future, and as I mentioned before, reducing the register usage of your kernel is very important, because it results in more copies of your kernel function being able to execute in parallel. And this is also called occupancy. The CUDA launch configuration API also returns a block number, and this is the optimal amount of blocks we should be using if possible. So the threads are an upper bound, the blocks are a recommended lower bound for performance. And this matters when you write kernels that process multiple items at once, for example, with a grid stride loop within. I'm name dropping this because we will be coming back to this. At that point, it might be interesting to still run multiple blocks, even though a single block may be fine, because otherwise we're not saturating the GPU. The GPU has 10 to 20 streaming multiprocessors, and each of those can keep multiple blocks of threads in flight. So it is, for performance reasons, interesting to have multiple blocks active at the same time. Another important aspect of writing kernels is synchronization. For example, here I have implemented a simple reversal kernel where we have our current index and we compute an index to swap values with by taking the length of our array and subtracting our current index. So every value is going to swap with a different value. If we execute this, I'm going to compare to the reference argument, so we have 1 to 100, we reverse it has to be 100 to 1, with the -1 being the increment. So this seems to be working fine. However, if, for example, a show function in here, which shows the value of I as running on the device, all of a sudden we see that the result is not true anymore. And this happens because of adding this show function, the order of execution changed. And this shows how this kind of swapping is only guaranteed to work when all of the threads are executing in lockstep, like physically at the same time. As soon as threads can be scheduled in different order, there might be conflicts of an item having been swapped already before the next thread reads it. And this is why threads need synchronization. So here, I first read my value, then I synchronize, and then I write my value. And this is guaranteed to work. So this kind of synchronization only works within a block. You cannot synchronize across different blocks. So again, if you're sending values to another thread, if they're running in the same warp, that generally just works. If they're running within a different thread on the same block, you need synchronization. If it runs on a different block, you're out of luck. There's no way to synchronize execution of the kernel function between different blocks. What this is going to do is this is going to make execution of your kernel function halt until all threads in the block have reached that point.
Question?
Sure.
If the sync threads is not reachable by all the threads,
That's bad.
basically that's just not.
Note how we didn't put sync threads inside of the branch. It's imperative that every thread reaches the sync threads function.
Stop or
Deadlock.
Yeah.
Yeah, depending on it's undefined behavior. It can deadlock in some cases. There's ways around. You can define name barriers. But generally, sync threads needs to be reached by all threads executing in a block. Another thing I mentioned was shared memory, which is one of the ways to communicate values between threads running within the block. And this often pairs with synchronization. So we can simply allocate a static shared array, which is a bit of shared memory within a shared multiprocessor that's statically shared. So we know beforehand how many values we want to allocate. In this case, 100 values. And we can simply do this by calling the CuStatic shared array constructor. The T element has to be the T argument has to be a constant, and in this case is the type of our input vector. And by running this, we can see that our reversal still works. So here, this is a typical pattern, not very relevant in the case of a simple reversal kernel, but it can often help where instead of every thread hitting global memory, if there's any reuse of values, you're only going to read the values from global memory once into shared memory, then use the shared memory as if it were a cache, and then finally, optionally, write back to shared memory. This is a very important pattern you can use to avoid global memory. Of course, the other common pattern is when you want to use this for communicating values from one thread or another, and this is what we're doing here. We're using the shared memory to write to at buffer at one location and then read at another location. Sometimes you don't know beforehand how many shared memory you need, and in that case, you can use the dynamic shared array constructor. And the difference is that my length argument can now be dynamic, so it's not a hard-coded constant anymore. And the trade-off is that when launching a kernel, we have to specify how many bytes of shared memory we can allocate. We should allocate. So this is a byte number. So size of is a Julia function that will return the number of bytes. If you want to compute this manually, you can do the length of a type multiplied by the size of the type. In any case, the shmem argument has to be a byte number. And the advantage of this is that now we need to compile this kernel only once, because otherwise we might have to compile multiple copies, one for every possible value of the static shared array constructor being invoked with. While here we can compile a single version and just change the shared memory argument and reuse that compiled kernel. The reason we still pass the length at runtime, which wouldn't be necessary per se, is that we can bounce check the accesses into that array. So if you index past the size of the dynamic shared array, the GPU will throw an exception or will throw an exception at runtime. And finally, another important construct for the things I want to explain next is atomic memory, where if we want to write or read from global memory, as we're doing here, we have allocated a sum container, which is a single element output, but we have multiple threads adding a sum into that sum container. If we were to do this without the add atomic, then one thread would trample over another thread, and the result would be undefined. So by adding CUDA.add atomic in front of this, we guarantee that our sum will still make sense, because all of the operations are going to be executed atomically. And this can be useful when you want to write, for example, a MapReduce kernel, or you want to reduce multiple values into a single output where you have some aliasing. Now, the add atomic doesn't generally support all types and all kinds of expressions, so it's somewhat limited to array operations, and it's somewhat limited to what types are supported. So if you define a custom element type that's, for example, 128 bytes, this will not compile on contemporary hardware. The size of your inputs have to be restricted to 64 bytes, basically. Atomics can be useful, but they're also expensive because essentially you're synchronizing the execution here, whereas normally the streaming multiprocessor can be executing many threads at exactly the same time. When you hit an add atomic, the GPU will have to serialize the execution and execute one by one, which can very significantly slow down your kernel. And then finally, another very useful feature when you'll be developing a kernel soon is structured output. So we support CuPrintf, which is a macro that you can give a typical C-style printf string to generate some output. Of course, C-style output isn't really convenient, so we also have the CuPrintLn function as the counterpart of the println function in Julia, which you can use with interpolation. However, it's limited what you can interpolate because ultimately we're still compiling down to a C-style printf. So you can interpolate simple things in there, but you won't be able to interpolate arbitrary values in there. And finally, as a very quick debugging aid, as I've shown before, we have the add CuShow macro, which you can basically stick in front of anything and it'll visualize both the expression you were showing and the value of it. And this can be convenient when debugging kernel execution without immediately having to jump to a full-fledged debugger. Even though this is a pretty dry list of features, there's many more that CUDA supports, and there is a dedicated kernel programming guide in the CUDA.jl documentation. So if you're interested in more advanced device-side features like cooperative groups or dynamic parallelism or warp level intrinsics, do have a look at the documentation. But I've selected a couple which will be useful for some example function that we'll be implementing next. But again, before getting to that actual implementation, I'll first be explaining some of the issues you will be running into, to be fair, because even though we're using Julia, not a DSL, we're using Julia, the language proper within our kernel definitions, there's still some restrictions with respect to what we can compile for the GPU. So you will be running into some compilation errors and some runtime errors, and I'm going to show the most common ones that you will probably run into today. So at the highest level, you cannot return values from a kernel. That's just not allowed. A kernel has to be a void function. If you do so, you'll get an error. There's obviously simple ways to return things from kernels, and the simplest one is just to use a single element array. So here my A array is a single element array, and my kernel writes to it. We also support so-called ref boxes, which, if you're familiar with Julia, is something that's used a lot. It can also be used to simply write to a single output value. One thing you might run into often are runtime exceptions. So Julia as a language is a fully dynamic language, and one of the consequences of that design is that all error reporting is delayed to runtime. So Julia will never fail to compile a function, but it might have reduced the entire function to a simple exception being thrown because of a typo, for example. But you'll only notice at runtime, which is a bit of a problem in case of GPU execution, because we cannot easily report exceptions that in the same way that happens on the GPU. So one of the consequences of that is that by default, you don't have any stack traces. So it'll just plainly show an error that mentions, hey, a runtime error occurred, no idea why, no idea where. The actual error will be trapped by the first subsequent synchronization. So this is just the GPU printing in the same way that I used the print functions before. It wasn't actually an exception yet because, again, of the GPU executing asynchronously. So the add CUDA was successful. The kernel was launched successfully. An exception occurred at runtime, and as a result, the first subsequent API call will actually trap and render the exception or the fact that an exception happened to your application. Because otherwise you might think that everything is just working fine because of never seeing an application on the CPU. So here you can see that the kernel exception triggered when we executed the synchronization. In order to get some stack trace information, you can start Julia with the -G2 argument, which enables additional debug information. That's fairly costly, and as a result, we don't do this by default. So if you run Julia with G2 and we perform the same function call, kernel call, as I did before, at least now we get some additional information where it happened, with a specific pointer to, for example, here the REPL definition where it happened. Do note that we still don't know which type of exception happened, it's just a exception happened. However, given the source code location, you could easily look up where that happened and you'd know what kind of exception happened. So this is the major, one of the major issues that we have with device-side code. The other one is that some IR patterns are not supported, and generally this occurs when doing very invalid things. For example, I wrote this function, tried to launch it, invalid IR error. Nowadays, CUDA.jl actually does its best to try and figure out why that was the case, and here it's pretty clear. Undefined name, use of thread ID. Instead of thread IDX, I typoed and I used thread ID. And if you would actually look at the code that's being generated, and I'll talk more about that macro later, you can see that the thread ID call was inferred to any. And this is generally a bad sign because it means that Julia has no idea what this function returns. And again, this is a property of Julia being a dynamic language. On the CPU, this is allowed. You can compile a function, you can even execute it, and you can define the thread ID function afterwards. So as a result, this is not invalid per se, but it is invalid on the GPU because it emits a kind of dynamic invocation that we don't allow on the GPU. For the GPU, everything has to be statically compilable. But again, all of the information you get has been greatly improved in the past years. It used to be much more painful. Nowadays, it's often fairly straightforward to figure out what happened. So here, another example, as I showed invoking a kernel with a string argument. Here's a slightly more complicated example where I'm invoking a function with an unsupported argument. And the unsupported argument, again, if you follow the hierarchy, .x is of type vector. We're using a CPU vector in our invocation. And this is just to show that if you pass invalid stuff to a kernel, the compiler will also complain. And here, that's because the bracket 1 is a CPU vector. We forgot to invoke the CU function or the CuArray constructor on that. You generally cannot use CPU memory with a GPU kernel. So that's about it. I've gave some basic explanation of the features you'll need and the issues you might be running into. So let's now try and port the root mean square error function, which we implemented as such with array operations. And for now, let's stick to a simplified version where we're only using a single block to compute this value in. So we'll be only using thread IDX function. For that, limits the size of your inputs to less than 1024 values because we're only using a single block. Use a single element array to store the result. So every thread is then going to be computing a minus b squared. And try to keep the number of API calls and kernel launches to a minimum. Specifically, that means that, for example, the 1 by n and the square root is also something that should be computed on the GPU if possible. Let's do this for 10 minutes or so, and I'll be walking around if there's questions or issues. Let's move on. a little. So I'll be showing my initial implementation of this function. I have my fallback definition for the CPU using array operations. I allocate some inputs, again, keeping them to 512 elements because we will be only using a single block initially. I allocate my GPU memory as well as my output container. And this may be the initial implementation I came up with. So what am I doing here? This thread is going to be executed by a single block. So I'm only allocating a number of threads here that corresponds to the length of my array. Single block. This simplifies execution right now. Every thread is going to query its current element that it needs to be processing, and I'm going to special case the first thread to do some initialization and finalization work. For example, here I'm going to check whether we are thread 1, and if so, I'm going to initialize my output memory, avoiding having to do a broadcast on the CPU to initialize that memory. Then, of course, we need to sync threads because this is not a single warp. These are multiple warps executing within the block. Next, I'm going to do my essential computations. I'm fetching two elements. I'm subtracting them, power of 2, and then I'm atomically assigning them, adding them to my output container. Again, I'm going to synchronize threads because then I'm going to special case thread 1 again to do the necessary finalization, namely dividing by the length of A and taking the square root. And this gives me the expected result after it finishes compiling. There we go. So it's the same result, 0.41, 0.41. So here I'm doing as much as possible within a single thread, within a single kernel, sorry, only launching a single block. Of course, as we've seen before, this does not work if we exceed the number of threads that we can execute at most on our device, which is 1024. So naively, you might want to generalize this by doing the kind of computation that I've shown before, where instead of just using the thread index, you are multiplying the zero-based block index with the block dimension to get a global index across the entire thread space. And then I'm using the occupancy API to determine the most efficient configuration of blocks and threads possible. This may be the straightforward generalization that you expect would work. Spoiler alert, it doesn't. Oh, this is suspiciously closed. In any case, it's wrong. Why is it wrong? Because this synchronization is only going to synchronize threads within a single block. I think I know where. Yeah, anyway. This is only going to synchronize threads within a single block. And with this configuration, we may be launching more than a single block. So our synchronization is insufficient because the finalization might happen before another block has finished computing. Or same with the initialization. The initialization may happen after some other block that does not contain thread 1 might have started executing already. So as such, this generalization is insufficient and we need to adapt it to the fact that we're using multiple blocks. And there's multiple ways to do that. For example, we could just move our processing back to the CPU, where we're initializing the memory using broadcast, and where we're ultimately finalizing the computation by doing this operation on the CPU. Also note that after generalizing this to use multiple blocks, I include this important check because the multiplication, the amount of threads globally may not be may be larger than the amount of elements, because the size of a thread block multiplied by the size of the grid might exceed the length of our arrays. So as soon as you start generalizing to multiple blocks, it's always best to include this kind of check, such that you don't index your inputs or outputs beyond their sizes. Another interesting way to generalize kernels to process multiple items than a single block would allow is by having every thread process multiple items, by putting a loop inside your kernel definition. For example, if we normally would have our index computation, and then we process a single item, if we change that by a while loop or a for loop with a stride, where the stride is the total number of threads in our grid, then we will jump automatically to the next slice of elements that has to be processed. So this is called a grid stride loop, because the stride of this loop is the size of our grid, the amount of threads that we launch, and we will automatically move forwards until we have processed the entire array. And this is especially important because it allows you to decouple the launch configuration from your kernel implementation. Previously, if you write a certain kernel that assumes it processes one element, you have to launch an exact number of threads matching that implementation. While in this case, we can launch such a kernel with one thread, in which case this loop will just process element by element, or we could change it to launching a single block of 20 threads or 5 blocks of 100 threads. The implementation will automatically adapt because we compute the stride based on the amount of threads that we launch.
Question?
Sure, go ahead.
If we do array processing like here and do with strides, is it better to do in blocks that are next to one another for cache? So like because stride will jump first element.
It generally does not matter. The only thing that matters, as I'll get to probably tomorrow, is that consecutive threads access consecutive memory operations when executing at the same time. Yeah. It doesn't necessarily matter the order in which the blocks themselves access memory. I'll paste the implementation of the kernel in Slack, and I suggest you try extending it to this grid stride pattern. So this is my current implementation. I'll show my implementation. So here I have the grid stride loop. Because we're only using a single block, I've simplified the stride to just the amount of threads. But if you want this to work with multiple blocks, then the stride computation would, as I've shown before, be constituted of the block dimension multiplied by the grid dimension, which is the number of blocks. But other than that, and this is just plainly the grid stride loop that I showed before.
Why would it be better to do the while sum in a normal variable and then do the atomic at the end? With zero.
Do what in a normal variable?
So create a new variable, add into that, and then have the atomic addition after the while.
Oh yeah, that's one of the optimization that, you're ahead of it here. So I went for the simplified version first, so I can fold the initialization and the finalization back in a kernel. If you're using multiple blocks again, then this wouldn't be possible. Yeah.
But at the end, with this implementation with the last code, you have the same number of atomic operation.
You have what?
The same number of atomic operation.
Yes, in this case, you would.
I don't see why it's going to move faster.
This is not about faster, this is about compatibility with larger arrays. Yeah. Speed is the next notebook. Speed is the next notebook. This is just for compatibility with large inputs where you need a grid stride loop to be able to deal with all of the elements that are available. So here I'm showing what the launch configuration of this kernel is. That's again asking CUDA what is the optimal amount of blocks and what is the maximum amount of threads we can launch. And as you see here, it suggests that we need to launch 112 blocks to make this kernel saturate the GPU. Whereas in this implementation, I'm only launching a single block of 256 threads. So we're underutilizing the GPU significantly, in effect, because we're only using one of the shared multiprocessors on the die instead of whatever is available. So let's generalize this. And this is the grid stride loop, where my stride is now computed as the grid dimension, which is the amount of blocks, times the block dimension, which is the amount of threads in my block. And now I can use the full launch configuration API to determine what is the maximum amount of threads I can launch, what is the amount of blocks that I need to cover all elements, and because I'm using a grid stride loop, we can clamp this to the minimum that the launch configuration tells us that we need to use. So in effect, if you're launching our kernel on lots and lots and lots of data, which would, for example, require thousands of blocks, because of using a grid stride loop, we can use what the occupancy API tells us, which was 112 blocks. So that's not enough blocks to cover all elements, but because we have this grid stride loop, this will automatically extend to all elements of the array. And this avoids some oversubscription of the GPU, where we're not launching hundreds and hundreds of blocks, where we actually would only need 112 in this case to fully saturate the GPU. So this is a very useful pattern in and by itself, where you're using, for element-wise operation at least, where you're using the occupancy API to query exactly how many threads we can launch and at least how many blocks we need. Launching exactly that number of blocks or fewer if it isn't required, having the grid stride loop adapt automatically to whatever inputs we throw at our kernel. And again, the emphasis here is that this is a realistic and a good basis to build more complicated operations on. So now let's benchmark this a little with larger inputs, because of course we can deal with larger inputs now. The RMC function is our function on the CPU. Benchmarking that takes a while, of course. (20 milliseconds). We will also benchmark this version when invoked with GPU inputs, which is essentially what we've been doing all day, the array operations that automatically execute on the GPU just by virtue of having been implemented, invoked with CuArray inputs. We have 340 microseconds. And now finally, let's invoke our custom kernel implementation. I'll remove the spoiler. 10 milliseconds. So at least we're slower than the CPU, but as you can see, we're a lot slower than our implementation using array operations. And tomorrow, or in the next notebook, I'll focus on how you optimize this kernel specifically. Because if you were to look at the execution profile of this kernel using Nsight systems, or using the CUDA integrated profiler, it would just show that the GPU is active all the time. So you might think, well, I'm saturating the GPU is running all the time. But at this point, that's because our kernel implementation is bad. So the next step is, how do we look into this kernel? How is it compiled? How is it executing? And how can we optimize the implementation to make the most use of what's available on the GPU? I'll finish off with some alternative approaches to kernel programming, but which I won't otherwise use in this course, but they're still worth noting. One is Tulio. Tulio is a framework that allows you to use index notation to express operations, which sometimes makes it possible to very compactly express certain element-wise operations or even reductions. Essentially, you're expressing in such an expression which dimensions to iterate over and which dimensions to drop and thus reduce over. So here, for example, I'm doing nothing, it's a no-op. If I'm dropping an index, I'm dropping j here, we will be summing over it. So let's show that. An array with ones is just going to retain those ones. If I drop an indexing iterator, then we'll be reducing over them. So here, for example, I drop all of them, which means I'm reducing to a scalar. And in addition to that reduction, you can use the pipe operator to put functions outside of the application, which makes it possible to, for example, here, the full reduction was 100, and then log10 returns 2. So this is a fairly powerful interface to express very compactly operations. For example, the root mean square error we can implement using Tulio as such, where we, of course, do the element-wise operation. We'll be reducing to a scalar, and then outside with the pipe operator, we put that we want to divide by the length and take the square root. So this is a very compact notation that nonetheless generates kernels for you. Best thing is, of course, that it's GPU compatible. I think you have to import kernel abstractions because it's built on kernel abstractions. There we go. So one of the issues with Tulio is that it doesn't have a great reduction implementation, and as a result, executing it would be similarly slow as our implementation. But for implementations that mostly focus on element-wise operations, where, for example, the reduction is only a minor part, this is a very powerful and compact way to write your own kernels using index notation. And as mentioned here already, the other popular package is kernel abstractions, which makes it possible to write kernels that are vendor neutral. It essentially defines a set of abstractions that map onto functions like thread index, or the block dimension, or the static shared memory, in a way that is supported by several backends we have in the Julia GPU ecosystem. For example, here I'm creating a global index, which will be computed by doing the whole block dimension times block index plus thread index dance we've been doing before. And we are using kernel abstractions.addAtomic, which will automatically select an appropriate atomic implementation. And this can be convenient if you know that you want to run on multiple GPU vendors, but nonetheless still need the flexibility that kernels have to offer, which you don't have with broadcast or other array operations. And lots of software has been built on top of that. Of course, it's still somewhat of a trade-off. So here I'm executing it on the CPU. I'm allocating CPU memory, and I'm using my kernel abstractions, RMSE kernel, given the backend CPU. And to allocate memory, we can use kernel abstractions .allocate, passing the backend along. As you can see here, that allocates a vector. We use the copy-to function to copy from our input to our device-specific array, which in this case is also CPU memory, but nonetheless, the goal is to write code that's vendor neutral and would work for the CPU or the GPU equally. We get an instantiation of our kernel for our backend, and then we can invoke our kernel given inputs, and instead of specifying how many threads and blocks, we specify the ND range, the n-dimensional range that we want to iterate over. So in this case, that's the size of A, and as a result, the I equals at index will return a value from 1 to the size of A, which in this case is a two-dimensional Cartesian iterator. This is much closer to the programming interface that I've shown with the kernels, where instead of using vectorized operations, you write a scalar function that performs the operation on a single element instead. And as a result, it can be convenient if you, as I mentioned, need the flexibility of kernels, but still don't want to sacrifice portability by using a single specific GPU backend. That comes at a cost, of course, because some more specific operations like warp collectives or cooperative groups that CUDA does support are not supported by kernel abstractions, which at this point is mostly the common denominator of functionality that's supported by all of the GPU backends and can also be supported by the CPU backend, because the kernel abstractions takes pride at also maintaining a CPU backend to validate computations with, or to be able to use both the amount of CPUs that a supercomputer has to offer and the GPU. But for the rest of the course, I will be using CUDA.jl specifically because it makes it easier to profile things and stick to the abstractions that CUDA-C has to offer. I think that in the interest of time, I'll keep it at this, and I'll keep the optimization and analysis part of the kernel notebook for tomorrow. But maybe we have some more time in case of some questions about what we've been doing today, maybe for 15 minutes still, and then we have to, yeah, all right. All right, good morning. And there's still some people missing, but I propose we should start because we have quite some things to cover today. So we're going to continue where we left off yesterday. I'm going to assume that everybody has a connection to the system, has a Jupyter running, and is able to activate the course project, which is unchanged. Again, I did comment out the package instantiate to make sure that it doesn't pre-compile over and over again, so I recommend you make that change as well as import the workaround for the Jupyter rendering issue. So we're going to pick up where we left off yesterday, where we implemented our root mean square error implementation. We did so with a simple kernel that used a lot of operation that turned out to be very slow. So today we're going to look at the kernel in question and see how we can optimize it. That's typically optimizing kernels involves a variety of techniques. Mainly, initially, you want to ensure that you're using parallel algorithms and not doing anything serially on a thread, of course, because GPU threads are actually fairly slow. You need to be using the parallelism that the GPU has to offer. And then, and relevant to our situation, we'll have to reduce global memory accesses by caching reads, for example, in shared memory, as mentioned yesterday, or by using appropriate mechanisms to communicate between threads when there's a finer-grained mechanism. So don't always go through to global memory, but use shared memory if possible, or use warp operations if possible to communicate between threads in a warp. It's also important to reduce register usage as much as possible, because with kernels that require fewer registers, the GPU will be able to launch more of these at the same time. And then there's some typical CUDA-specific optimizations, like avoiding thread divergence, which is when threads within a warp branch differently. You basically want all the threads in a warp to behave almost identically, or at least execute the same code. They can still operate on different data, but the instructions that they execute should be similar. And of course, there's also optimizations with respect to optimizing the memory accesses, making sure that the memory can be cached optimally, and so on. For that, we're going to go back to our case study, the root mean square error, which we implemented yesterday as follows. Again, with the grid stride loop in there to make it resilient to launch configuration changes, with the initialization and the finalization outside of the kernel. And other than that, lots of atomic operations in our loop, which are probably going to be problematic, as you might guess. So let's start with benchmarking our implementation. I should also note here that here I provided a convenient pattern where I have an outer function that can be invoked on the host with CuArray inputs, and then within we define our kernel. So the kernel is, as it were, a private function within our host function. And this is interesting because it's a maintainable pattern where you can, within the kernel, rely on specific information, for example, depending on how this kernel is going to be launched. As if it were, it shields people from trying to reuse your kernel in a way that would be incompatible. So you can take assumptions on, for example, the launch configuration within your kernel that only hold when it's invoked by this outer function. So this is a neat kind of way to package up a kernel and the associated host functionality in one easily reusable function for other users to call into. So if we benchmark this, we have 9.8 milliseconds, and our baseline implementation, which was the optimized implementation with the lazy broadcast being passed into a reduction, performed on the order of hundreds of microseconds. There it is, 170 microseconds, which you should note is half what we had yesterday, because here we're using float 32 now and not float 64. Question?
Benchmark, you did use sync because it was reduced at the end?
Yes. So here in the benchmark, I'm not adding CUDA.add sync, because we're always reducing to a scalar at this point. So we have to wait on the GPU anyway in order to access the results of this computation. If our function would be returning an array or another operation that could be executing asynchronously on the GPU, we would have to benchmark with CUDA.add sync. If you're not sure, it's always safe to add that synchronizing a GPU which is idle is a very, very fast operation. So it wouldn't mess with the benchmarks. So you might initially use the integrated profiler to have a look at the performance of our kernel, or at least the performance of our outer function that we've implemented. But as you'll see after it compiles, here we see that the GPU is actually being used all of the time during our execution of the benchmarks. So with respect to optimizing the application, there's fairly little to do, because even if we would trace this in Nsight, you would see that the GPU is active all the time and this kernel is actually actively working all the time. So you might think that this is a good way of using the GPU, and it is from the application side of things, but it isn't, because this kernel is slow. The kernel itself takes 10 milliseconds, which is an enormous amount of time for this little data. So let's have a look at how to optimize the kernel itself. And for that, we have to use the other tool from the Nsight profiling suite, which is Nsight Compute. Nsight Compute is a tool that's going to give you insight within the execution of a kernel. The way how you use Nsight Compute is slightly different. With Nsight systems, you ran Julia under Nsight systems, and when you did CUDA.add profile of a bit of code, you got a report file which you could download to your host and then open in the Nsight systems UI. With Nsight Compute, you again have to run Julia under Nsight Compute on the compute node, but crucially, you have to have the user interface connect back to the target system so that it can actively look into the process, what's happening, and extract metrics and so on. This is sadly fairly tricky to do with the supercomputer setup here, because we have spawned up a compute node which you cannot easily SSH into without requiring lots of setup that would take too much time to set up for everybody for this course. So instead, I'm going to rely on screenshots to show what's happening. But if it were configured, as for example it is here on my desktop, this is VS Code running the Jupyter plugin, so it's again the same notebook as you've been seeing all along. But however, I have configured a kernel that doesn't just launch Julia, but launches Julia under Ansys. And as soon as you perform any API call, initially the process will hang and it will prompt you to open it up Nsight Compute to connect to your system by clicking the connect button, which is now grayed out because I'm connected already. Select your host. It's going to SSH to your host. It's going to give you a drop-down where you can select the process to connect to. All of that is also explained in the CUDA.jl documentation with screenshots. So if you need to set this up, have a look. And then once it's connected, initially we're going to want to disable the break on API error, because CUDA on purpose triggers a couple of API errors, and otherwise the process would hang. And then under the profile menu, if you select auto profile, every kernel that you will execute in your Julia session will automatically be analyzed by Nsight Compute. This is not something you want on all the time. For example, if you want to switch between development, benchmarking, and analysis, when you run under add benchmark, you want to disable the auto profile, because otherwise every iteration of the benchmark is going to get analyzed by Nsight Compute, which is extremely slow. So here I've enabled auto profile. I've executed this cell, which contains our kernel implementation function, which performs initially a broadcast to initialize the memory, and then our kernel. And here you can see both kernels being detected and analyzed. So crucially, the estimated speedup is a good hint of what to look at, where you should focus your efforts. So the broadcast kernel is already at a 99% speedup, so there's little to optimize there. The root mean square error still has some room left. And conveniently, Nsight Compute is going to give you a bunch of recommendations with lots of explanation, especially with the potential estimated speedups that could happen if you follow this advice. If you click on any of those, you'll be switching from, currently we are at the summary page, to the details page. And the details page contains all of the results of the analyses. The analyses you can configure over here with the metric selection. Currently, and by default, it selects full, which means it's going to gather as much metrics as possible. And all of those gives you a whole bunch of information. For example, at the top, we can see under the GPU speed of light that we have very low utilization rates of what the GPU has to offer. We're only using 1.3% of compute throughput, only 1.4% of memory throughput. So this is an abysmal kernel, really. All of those can also expand. So if you click on here, you'll get nice charts which visualize again how bad our kernel is. Again, all of those always go to the summary page, follow the recommendation. You can expand some of those. You can get additional details and charts and metrics and so on and so forth. Again, I'm not going to do this interactively because tracing the kernel actually exchanges quite some data between the host system and the target system. Just tracing this kernel was a couple of hundreds of megabytes, so I cannot realistically do this to my home system, which I'm currently connected to. As a result, I'm going to switch back to the notebook I've prepared where we've got some screenshots. So as I mentioned, running under NCO mode launch, slightly different to how Nsight systems worked. We select auto profile and then executing any operation would otherwise trigger Nsight compute and show the kernel in question. So if we execute our root mean square error, one of the top issues is global memory stalls. If you go to the NVIDIA documentation page, all of those are detailed even further. And one thing you can also do is have a look at the source code to try and figure out where exactly those stalls came from. And there you can correlate the PTX code or the shader assembly code, which is an even lower level code, with the stall reasons. Sadly, our debug info emission isn't on point yet, so you'll have to look at the PTX code and you cannot yet look at the Julia source code. We're hoping to improve that so we can just annotate the stall reasons to whatever happened in source code, but currently you'll have to look at the PTX code. Luckily, it's fairly readable. So here we can see a load from global memory, another load from global memory, in addition, a subtraction, a multiplication, and finally an atomic add. And that, of course, corresponds very nicely to our loads from global memory, a subtraction, a multiplication, and an atomic store. So that's basically the code for our hot inner loop. Of course, the initial global loads we cannot get rid of because it's an element-wise operation. We're loading memory, we need to use that memory, so there's no way to get rid of that. There is, however, a way to improve how the atomic operations are being done. Currently, for example, we're doing an atomic operation within the loop. At the very least, it should be possible to move that outside of the loop, avoiding every iteration to perform an atomic operation. But beyond that, we can also go a step further and avoid that every thread has to do an atomic operation. I propose that you all try implement the first optimization as a warm-up. Take the implementation, move the atomic operation outside of the loop, and notice how the performance does or does not improve. And then beyond that, I'll explain how we can do the trickier part, namely making sure that not every thread has to do an atomic operation. Assuming that nobody has any issues, let's show the initial optimization because, of course, it's not particularly difficult. Instead of doing the atomic operation within the loop, we'll be first accumulating into a local value. A value is fine because we're just accumulating a value for this thread. And then finally, we're going to accumulate that local value into the global buffer. So these are the only changes required. Performance, however, is a very big difference. So let's look back. The performance was, okay, this is not great. Performance was 10 milliseconds. So after moving the atomic operation out, we're at 350 microseconds. So that's, well, yeah, a huge improvement, of course. And we're even getting close to the performance of the array operations already. So now if we look back at Nsight Compute, the global load stalls and the initial stall reasons have disappeared, and what remains now is a stall train. So it's still a type of stall, but it's a slightly different type of stall. And if we look at the documentation, NVIDIA tells us that this is a stall that prevents the kernel from exiting, and as a result, it's likely related to the code that our kernel executes at the end right before returning. And this, of course, matches with the atomic that we're still doing, which we do at the very end of every thread. So the next step is to try and avoid more of those atomic operations. And the way we're currently doing it is that every thread in a block is going to perform an atomic operation. So let's try and first accumulate within the block using shared memory, for example, and then only have a single thread accumulate into global memory. And again, this is one of the principal techniques where you want to avoid that all of your threads hit global memory. If possible, you have to use a more local communication mechanism to store into shared memory first, or or use warp intrinsics first before hitting global memory. So the way we generally do so is using an atomic reduction, and a parallel reduction. So again, it's fine to first perform our grid stride loop on a single thread and try to accumulate as much values as possible, but then instead of going straight away to global memory, we'll first try and send that value over to other threads, and again reduce it in a way that we come up with a single value to reduce within our block. And one way to do this is with a so-called tree-style reduction. So if we allocate a buffer of shared memory where every thread writes its value into, then we can have a for loop which, in a tree-style fashion, every thread is initially, or half of the amount of threads is initially going to be reducing a value with its neighbor. And at every step, half of the threads drop away and fewer values have to get reduced again, until ultimately, after log n steps, we get a single value on thread one within the block, that is. And then finally, only one thread has to write that to global memory. So the goal is now to try and implement that. Basically, you're going to retain the structure of the loop where you've got your value that was reduced by a single thread. And then we're going to perform a parallel reduction, sending those value in a tree-style reduction to other threads until a single thread in the block retains a value to write to global memory. I'll send my initial implementation on Slack so that you have a good starting point with the local value reduction. And then I propose to spend some time on trying to optimize this. I added a hint here on how to implement that loop. So basically, you want to determine a stride. Initially, the stride is 1 because every half of the threads is going to access the value of the thread at current thread ID plus the stride. And then the stride always doubles until there's only one thread left. Let's move on to the solution for this. And this is generally pretty tricky to implement at the first time. I mean, these parallel algorithms are a different kind of thinking. They're also tricky to debug. But the solution I came up with here is, so we retain the grid stride loop, producing a single value. Now we're going to reduce that in shared memory. I'm immediately using dynamic shared memory, where the size of my dynamic shared memory is the amount of threads, because every thread is going to write its value into dynamically shared memory. And I'll explain later how we properly initialize this. So as I mentioned initially, you can start with this being static shared memory with 1024 elements, but it actually can be smaller and bounded by the number of threads. So then every thread writes its current value into shared memory, and we need to synchronize an execution barrier to wait for all threads to arrive. Then we perform the parallel reduction as I mentioned. So we start with a stride of 1, and the stride is multiplied by 2 at every iteration. We check using the suggested code whether the current thread still participates in the reduction. And if it does, we look up another thread's value, thread plus our current stride. That should be stride, not S. and we save it to our own spot in shared memory. And then finally, once the stride exceeds the block dimension, which means that the reduction has completed because we would be indexing outside of our shared memory buffer, we know that thread 1 has a fully reduced value in shared memory, which means that we can then have a single thread, thread 1, write that reduced value into global memory using an atomic operation. So essentially here we've avoided having every thread perform atomic operations, and we reduced it to only a single thread performing atomic operations, which is another reduction by a factor of 1,000. Sure.
So there are two or three things I don't forget, but one of them is that at the end you say a single thread will do an atomic operation,
Mm-hmm.
right, into the memory. But if a single thread is trying to write to a memory location, it doesn't need to be atomic.
It is, because so the question was whether this operation needs to be atomic if it's only a single thread operating on that shared memory location. It is, because the thread number here is the thread index within the block. It is not the global thread number. There may be other blocks executing in parallel on different shared multiprocessors. So this is purely thread IDX.x. It is not the computation we do here, where we compute a global thread number by taking into account which block we're currently executing on.
But then there is something I'm not fully clear with our implementation. If you can get back to the graphic. So here, if you synchronize horizontally all the threads, you don't have to use atomic operation actually, because you never have to thread if you use like a buffer to store the interleaved, like the intermediate value. If you horizontally synchronize all of the threads, you never end up with two threads writing into the same memory location, but you have to synchronize them. But so you don't need the atomic operation.
Yes, so the question is whether we don't need atomic operations to reduce these values because we're synchronizing at each step. And that's also correct, but we note that we aren't doing any atomic operation within here. So we are just writing into shared memory without having to use atomic operation, because as you noted, there are no conflicts in here. Every thread is only ever writing to its own location in the shared memory buffer, and it's only reading from a location where we know that that thread isn't active anymore at that time. So because of that synchronization barrier, and because of that structure, we do not need atomic operations on that shared memory during the reduction, but we still need an atomic operation here, because other blocks, which by themselves have been doing their own parallel reduction on a slice of the memory, might still be concurrently writing to our single output value. And in order to avoid multiple blocks overwriting another block's value, we need to use atomic operations there in the final reduction.
Sync thread synchronize thread from different blocks.
Within the block, yes. Sync threads only ever synchronizes within the block. It's not possible generally to synchronize threads across other blocks. Otherwise, if we could do this, we could probably do a similar reduction across all blocks, but we can't do that. So the other thing is that my implementation here is actually only going to work for power of 2 inputs. Generalizing this to non-power of 2 inputs is a little tricky. It just makes the indexing a little more annoying. And in fact, while doing so, I'll also pick a better performing optimization. There's been lots of research and documentation on this. For example, there is a white paper by NVIDIA how to optimally implement parallel reduction, because, for example, there's still some issues with this. We get very sparse, not sparse, we can very memory loads that are far from one another. For example, here we're going to be loading element 1 and element 8, which probably triggers a whole cache line to get read while all of the values in between are not being used. So it's possible to restructure this loop in a way that we more efficiently only access consecutive memory operations. There's other optimizations like avoiding bank conflicts as well. So in order to not bother with this, I'm just going to pick the best optimized implementation from that pretty old white paper, which is similar, but it performs better and it also handles non-power of 2 inputs. And this is generally the implementation that we use in CUDA.jl's MapReduce as well. The other thing I need to mention is, as I said, I'm using dynamic shared memory. I'm not using static shared memory. The problem with that is that we have to inform CUDA when launching a kernel how much shared memory we need. Because again, it's dynamic shared memory. It's not pre-allocated during compilation of the kernel. It's only determined at launch time. The problem is that shared memory also influences how many threads we can have in flight, in the same way that if a kernel uses lots of registers, fewer threads will be able to be active at the same time. If a block uses lots of shared memory, similarly, we'll only be able to have fewer blocks at the same time active within a single shared multiprocessor. As such, the launch configuration API needs to know how much shared memory we will have to allocate. And you can do so by setting the shared memory keyword argument to the launch configuration API. You can either set that to a constant, for example, 1024. However, in our case, the amount of shared memory depends on the amount of threads we're launching. But the launch configuration is determining the amount of threads we can launch. So there is a dependency here. And in order to make it possible for the launch configuration to accurately take into account how much shared memory will require, instead of setting shared memory to a constant, you're setting to a callable function that takes the amounts of threads as input and returns the amounts of bytes we need. By doing so, the launch configuration can accurately and optimally determine how many threads can be launched, how many blocks should be launched at minimum, and we can pass the same amount of shared memory to our kernel invocation. Relatively advanced pattern, but nonetheless a very useful pattern that you will require when using dynamic shared memory in a non-trivial launch configuration. That's why I definitely wanted to mention it here. So let's benchmark this. So our initial implementation, our final implementation was around 300 microseconds, and now we'll be getting 100 microseconds. So at this point, we're even outperforming our implementation using array optimization, which performed at around 150 microseconds. So this is also a nice example why it might be interesting for very hot kernels to jump from executing it with array operations to implementing your own custom kernels, which takes some additional domain knowledge into account, or in this case, just simplify the code that's being generated slightly in order to, for example, consume fewer registers. Question?
Here you want a kernel that is faster than the kernel abstraction, but if you are using kernel abstraction, you get like a mini architecture.
We're not creating a kernel that's faster than kernel abstractions. We're writing a kernel that's faster than array operations. If you would implement this using kernel abstractions, I expect this to perform identically. There is no reason that writing a relatively simple kernel like this using the vendor-neutral kernel abstractions API is going to perform any slower. Kernel abstractions, however, for example, does not support dynamic shared memory, so you would have to use static shared memory with the upper bound of 1024 threads. But again, with a simple kernel like this, I don't expect that to realistically impact performance.
So my question wasn't about performances, but about the architecture you can target. I was wondering, so if you use the array operation, then using the kernel abstraction in parallel. Correctly, you can take any architecture, but as soon as you start really diving into writing your own kernel with CUDA.jl, how can you port this easily to other architecture? Because you went away from this kernel abstraction thing. So can we run this code easily, like on AMD GPU, Rocket, or?
So if I understand correctly, the question is whether moving to a CUDA.jl specific kernel still allows vendor portability. Well, syntax-wise it doesn't, because of course we're using CUDA.jl here. But the way we're doing things here is fairly similar across GPU vendors. So this kind of parallel reduction is going to be working as well on AMD GPUs, on Intel GPUs, on Metal GPUs. Some things might be different. For example, I mentioned the optimizations of the use of shared memory to avoid bank conflicts. Something like that might be CUDA specific, might not matter as much on AMD, or a different optimization might matter more on AMD than it does on NVIDIA GPUs. And our solution, work in progress for that, is to A, implement this kernel using kernel abstractions.jl, which gives you the platform neutral syntax, and then B, figure out a language of kernel side abstractions that can then be implemented optimally. For example, this parallel reduction could be a kernel reduce function, where you reduce within a kernel, as opposed to calling the reduce function on the host, which does a reduction across the entire device. And that should make it possible to implement all of the performance crucial details that you have between vendors in a way that still gives you a way to implement these kernels in a vendor neutral way. However, those details aren't generally going to be the big performance difference. So a parallel reduction kernel like this is expected to behave and perform perfectly well on all GPU vendors. This is more like a GPU programming pattern than it is a CUDA-specific programming pattern. I'll be showing some other tools that can help you optimize code. And one that I already mentioned briefly is code reflection. I've shown to some people the add device macros we have in Julia, add device code macros, and these are very similar to the code macros you have in base Julia itself. So in base Julia you have code LLVM, code warrant type, code native. In CUDA.jl and in many other backends, we add device underscore to that to note that we're not going to show the host code that executes on the CPU, but we're going to be showing the device code of any kernel that happens during execution of that code. For example, code warrant type can be used to have a look at the type invert code. So here I'm adding device code warrant type before an array operation that performs broadcast, and as a result, here we can see the implementation of broadcast. And this, for example, as you already can see, is a little more complicated than if you would just write an element-wise kernel yourself. That's why sometimes even replacing simple array operations with specialized kernels can give you a very minor performance improvement. For the others, I'm going to be using a much more simpler kernel, namely invoking the identity function with a non-argument. So this is just a return void function. With device code LLVM, you can look at the LLVM IR that's been generated. And this is generally the most useful level to be focusing on when you're micro-optimizing kernels, because yes, this is machine code, basically almost, but it's still very readable. For example, you'll be able to spot exceptions being thrown from the LLVM IR pretty conveniently. It also has debug information, so here in the comment you can see which Julia code this code corresponded to. Below that, we have the PTX code, which is the virtual instruction set architecture, meaning it's similar. The syntax and all is similar for all NVIDIA GPUs. The specific code that's being generated can differ from one GPU to another. That's also why you can see that the target here is specific to the GPU that we're working with, but the code will look similar across all vendors. And below that, of course, you have the machine-specific, the GPU-specific machine code, and here even the instructions will look different across GPU generations and GPU models. I also want to delve a little deeper on kernel introspection. As I've mentioned before, with the launch configuration API, we used add CUDA with launch equal false. And this gives us a callable object, which we can then use to invoke the launch configuration API. But there's another couple of things we can do with these callable objects. We can call the CUDA.registers function, which tells us how many registers this kernel will use, or we can use the CUDA.memory function to show us exactly how much memory our kernel is using. This is local memory, which is when registers are being spilled, shared memory, which are of course the static shared arrays you've already worked with, and constant memory, which is another special case of memory that we don't really support in CUDA.jl. Having a look at the registers is useful because sometimes decreasing the amount of registers that your kernel uses can have a drastic impact. For example, this is a chart that Nsight Compute shows you, a roofline chart, and not actually a roofline chart. And anyway, it shows you that depending on how many registers each thread uses, the multiprocessor can significantly impact the warp occupancy, namely how many threads can be kept in flight. So much so that even reducing a single register can double the amount of threads that can be active at the same time. So that's why it's sometimes crucial to reduce register pressure, ideally informed by a chart like this, because sometimes it may not matter whether you reduce registers or not. And you can also see this by calling the max threads function, which shows you how many maximum threads we can launch. And in here, 1024 is the same as the device limit. So obviously, we shouldn't be optimizing this kernel, but it's also a kernel that doesn't do anything and just returns void, so that's expected. So again, let's go back to our optimized RMSE kernel. It currently requires 22 registers, and it already uses the device volume. So here, reducing memory pressure won't help realistically because the amount of threads that we can keep in flight at the same time is the device limit already. Nonetheless, let's still show you what you could do by explaining some techniques that may matter to other kernels. So the easiest way, and also the worst way to do so, is by just passing max regs to add CUDA. And this will cause the CUDA compiler to try its best as possible to keep fewer registers alive. This can be convenient when you want to shave off just a single register to get below that threshold. However, it often does so by spilling registers to local memory. And in fact, local memory is just global memory that's thread local. So as a result, it's very slow and it generally will impact performance very negatively unless, again, it, for example, doubles the occupancy of your kernel. So if you already optimized your kernel and Nsight Compute tells you, well, you need to shave off one more register and you're failing to do so, it might be convenient to use max regs here and just put it below that threshold and double the occupancy. I also want to note that it's generally not great to embed this in applications. This is the type of micro-optimization that not only depends on the device in question, it also depends on the CUDA toolkit. It also depends on, for example, what types you're using as the inputs to your kernel. So if you've written a very generic kernel, which can be invoked with a variety of inputs, as we've been doing all the time, If you then hard code this max regs number based on some analyses, it might help for your case, but it might not help for other cases. So this is something you would do when you're finalizing code and you need to prepare a run and squeeze out as much performance as possible. A better way generally to avoid, to reduce register usage is by simplify the codes that being generated. And for that we can use these, we can use the device code LLVM macros and other tools to have a look at the codes that being generated. So I propose as an exercise to play with these macros, to take your RMSE implementation, to have a look at the generated code, try to figure out, is this excessive code, could it be simplified, and try to improve your implementation and lower the amount of registers that's being used. And maybe for simplicity, I'll also share the implementation that I had came up with that does the power of 2 fast reduction as a starting point. So let's have a look at how to optimize this kernel. The easiest way to do so is by having a look at the LLVM IR. And I have 2 relatively generalizable suggestions here to improve register usage. One is to avoid needless exceptions, and the other one to avoid needlessly wide types. The last one is, well, both are fairly Julia specific. Exceptions can get introduced everywhere, for example, bounce errors, conversion exceptions, and so on and so forth. And oftentimes, especially in the case of bounce error, you have enough information or guarantees that you cannot access a certain array out of bounds, and then you can add inbounds to avoid that exception. The other one is to avoid needlessly wide types. That's because in C, many types are by default single precision or 32 bits, integers as well, while in Julia, integers on 64-bit machines are 64 bits wide, and the default floating point literals are 64 bits wide as well, which can lead to unnecessary promotions and as a result, higher register use. Removing the bounce checks we can do because, for example, here we know that we already are bounded by the length of A, and we checked in our host level implementation that the size of A matches the size of B, so it's safe to add inbounds to this entire loop. Similarly, we know, again, this is because we exactly know how this kernel is going to be invoked, we know that we always have a sufficient amount of dynamic shared memory, so we don't have to bounce checks. And this is interesting. This is an add inbounds that added to a constructor. And that's because the CuDynamic shared array constructor is also going to check whether you provided enough shared memory to construct such a dynamic shared array. So that's why you can curiously add inbounds to the constructor, but you can also add inbounds to all of the uses of that shared memory buffer, because those are checking whether thread is inbounds given the size of the array. Similarly, here we can also add inbounds to our loop, because we know that this parallel reduction is correctly bounded against the maximum number of threads. And finally, of course, here we also know that C will have 1 element and that the shared memory will at least have 1 element. In general, though, it's not recommended to just add inbounds at the definition side of your kernel. You should do so smartly based on where you know that you cannot go out of bounds. The cost of these is not insignificant, but at the same time, running into bounce errors at runtime, it's much better than silent memory corruption or illegal memory accesses, which completely kill your session if you roll into them. However, the number of registers reduced significantly from 26 to 17. So as you can see, it does have a significant impact. Another, even more subtle conversion is by using, for example, int32 everywhere instead of literals that are by default int64. So this also applies to, for example, subtracting by 1, or here initializing by 1. Generally, again, you should be careful with these kind of optimizations because it's, especially with linear indices, here we're computing a linear index, it's easy to go past the limit of, say, 4 gigabytes, or just when you're using large arrays, int32 will not cut it. Of course, for, say, the stride of a parallel reduction, we know that we will at most ever be processing 1024 threads, so this can be safely int32 all the way. But for other indices, you should be mindful how you're invoking that kernel and whether it makes sense to demote everything to int32. Always validate that it does improve performance or register usage. But see, we did, however, manage to drop it further to 14 registers. And at this point, we can invoke CodeLLVM. I'm adding debug info equals none to make the output a little more sparse. And you can see that the generated code is now very compact. We have not that many instructions, it's fairly straight-line code with only the branches that we accept, and there's no trace of exceptions whatsoever anymore. So at this point, this code looks fairly well optimized. And finally, I want to briefly discuss memory coalescing. So one of the optimizations that I've briefly mentioned yesterday is that it's important that consecutive threads access memory consecutively. And this is on the CPU true as well, but on the CPU you have temporal locality in a loop. If you're accessing element I, you want that the next element is the data right next to it. And generally on the CPU, you do so when iterating an array to making sure that the leftmost index of an array indexing operator should be the one that changes the quickest. And that's because Julia is column major. The same holds true on the GPU. So GPU arrays are also column major. However, on the GPU, we should also think of spatial locality. So when a thread is accessing a memory location, other threads that are executing at the same time should be accessing consecutive memory locations. So you shouldn't be thinking of a loop within a thread. You should also be thinking of all of the loops in the warp accessing memory that's spatially nearby one another. And let me demonstrate that with an example. So here I allocate some data on the CPU. I upload it on the GPU, and again, I define a quick XP kernel. And here, we're accessing our input in a way that the rightmost index is the one changing the quickest, because the rightmost index is J, which is the thread index, meaning that the different threads in a warp which will be executing at the same time, will not be accessing consecutive memory location, because in order for memory location to be consecutive, we should only be chaining the most leftmost index of the array expression. So here the thread index is bound to the rightmost index. Let's benchmark this. "43 microseconds, and that's now switch it around. We're now I at the thread index, which is the leftmost index expression used in the array, and we can see that performance significantly improved. There's a factor of 3 difference. So essentially the guideline here is that the index that's bound to your current thread index should be the leftmost one used in array indexing expressions. And as you can see, this is crucial for performance. Now, generally, we wouldn't implement a function like this. We would be using a linear index. So even though x and y are 2-dimensional, here we're just indexing it using a simple linear index, i.e. a number. And the benefit of that is that with linear indices, we get this for free. So if the linear index changes by 1, then we will be addressing consecutive memory locations. And as a result, because our linear index is the offset in there is the thread index, we will be accessing consecutive memory locations across the threads in a warp. And as you can see here, the performance is similar. I want to note, and this is something I mentioned yesterday, the difference between using a for loop and a while loop. Here I'm expressing my grid stride loop using a for object. For loops aren't slow per se. What is slightly slow is the step range we're constructing in here. So this expression actually constructs what's called a step range, which has a lower bound, an upper bound, and a stride. However, it does some more, it offers more semantical guarantees than a single while loop where you just take I and you add the stride to it. Has, for example, it does some overflow checking. So if you will look at the generated code here, you will see that this potentially throws an overflow exception, which is something you wouldn't get if in a while loop you're just adding a value to an index. As a result, this can be slightly slower because it consumes a little more registers, and this is also why I have been using a while loop, partly for because it looks slightly cleaner, partly because it generates slightly better code. This is a very micro optimization. It's not something you should bother with initially, but it's one of those patterns that if you look at the generated code, you might see an exception and not knowing where does that overflow exception come from. Well, it might be coming from the step range objects that's being constructed by the loop. And that's why in my previous examples, I've always, actually, I can show you. If I uncomment the benchmark here, evaluate this, look at the generated code, we can see that lots of code is being generated, all step range code, and ultimately an overflow handling. If we get rid of the step range and look at the generated code, all of that is gone, much simpler. Again, might not matter depending on your application, depending on what your kernel is waiting for, but it is a kind of micro optimization that might be interesting when squeezing the register usage of a kernel. And with this, I end the kernel optimization notebook. I propose we take a break, and then afterwards I have 3 shorter notebooks on more advanced usage of CUDA. All right, what remains are 3 notebooks on some more low-level uses of the CUDA libraries and the GPU stack, some of which may not be relevant to you, others might be very interesting. Out of the interest of time, I'm going to teach those without many exercises, so that we, after lunch, can hand the mic over to Samuel with his part of the course. So in the first notebook, I want to give an overview of the CUDA stack again, because I've sometimes briefly skimmed over the different levels that we have. So basically, CUDA is built on a CUDA driver. Above that, you have the CUDA runtime, which is similar, gives a slightly higher level view of the CUDA driver. And then you have a bunch of CUDA libraries like cuDNN, cuFFT, and so on. And CUDA.jl allows you to interface at each of those levels, depending on the granularity that you need for your operations. Some of our application libraries, specifically cuDNN and cuTensor, cuDNN is fairly popular, are not part of the CUDA toolkit itself, and as such we have also recently moved this out in a separate package. So we only ship and offer wrappers in CUDA.jl for the packages that are included in the CUDA toolkit. cuDNN and cuTensor, even though they're part of the same CUDA.jl repository, they're not imported by default, in part because of load time considerations. So I'll start with the application libraries. For example, cuBLAS and cuRAND. You can interface with these libraries at different levels, generally. At the highest level, we use these libraries to implement standard library functionality, like as I'll show here, the linear algebra.xpy function. So if we invoke this function with a CPU input, we get the expected answer. If we just switched it over to a CuArray, still calling this standard library function will give you an answer based on cuBLAS. Sometimes we don't implement the array operation in question, and then you might run in a variety of errors. As I've shown in the array operations notebook, that may be a scalar iteration error when the implementation in base of XPY is implemented in terms of for loops, or a pointer conversion error when the implementation tries to dispatch to, say, the CuBLAS library. But if it is implemented, CUDA.jl generally provides two implementations. One, and that's built on top of libraries like cuBLAS or cuFFT or whatever. And sometimes, if we've had the time to implement a native version in order to support a broader set of inputs type that are otherwise not covered by the library below. You can, of course, just choose to interface with cuBLAS directly. For example, we can do cuBLAS.xpy. This XPY function is actually not something that cuBLAS defines. It is a wrapper that CUDA.jl defines to bridge the gap between the C library and the user interfacing with the operations. For example, here we provide a single method that will automatically dispatch to the correct C method, which is type specific. Sometimes we don't provide such a method because we haven't wrapped the entirety of the C library, and you might have to go to the C level and actually call the C level function. Luckily, we did provide auto-generated wrappers. So every C function that you can find in the cuBLAS documentation is available in CUDA.jl. And this can be very convenient when porting existing GPU code, which uses a variety of application of library calls, to Julia, because we will always support every C function that the library has to offer. Of course, at this point, you can see that the calling convention is becoming more and more verbose, because this is how C implements things. You have to send a pointer, a stride, a length. All of these things are normally encoded in array objects, and we automatically get out of the array and forward to the C library. Of course, if you're interfacing with the C library directly, you have to pass all of those values by yourself. Also note that many of the library API calls require a handle argument. This is, if you want it, an instantiation of the library and data that's associated with calling the library. And you can always get a handle by just calling cuBLAS.handle or cuFFT.handle. And this will give you an opaque handle object, which you can then pass to the C level library functions. Again, generally, there's no need to use these unless you have a very specific need or if you're porting code. Otherwise, use the higher level functions, or even better, use a standard library integration such that your code will keep working on different platforms. One special library is the CUDA driver library. The CUDA driver library represents all of the low-level functionality that's involved with working with CUDA. Let me first clear the output again. There we go. Similarly, the CUDA driver library can be accessed at either the C level, which is very low-level functions, or one level above that, wrappers that we've created to work with CUDA driver library. There's no standard library integrations, of course, because there is no CUDA standard library and base Julia. So I'll be showing some of these higher level wrappers that may be convenient when writing CUDA code. For example, with the devices function, you can iterate devices that we currently have available on the system, and we can get a hold of one of these devices either by iterating the devices object or by just calling CUDevice with a device number. Normally, Julia is one indexed, but here I've chosen to stick with the CUDA convention of labeling devices starting from 0 to make it easier to port code. These device objects you can use for introspection. For example, we can have a look at the compute capability that our device have to offer. We can have a look at the total memory that our device have available. And we can also query attributes. And these attributes, I've already shown with this one, which is the max threads per block. People have been asking about how much shared memory can I allocate. That's also device attributes. There's plenty of device attributes. If you just do step completion, you can see the entire list of things you can query about this device. All data in a CUDA process is bound to a CUDA context, which encapsulates all of the objects that you've allocated and so on and so forth. Normally, it's possible to instantiate new and more contexts. However, on this cluster, we can only create a single context. As I mentioned before, we can only interface with only a single process can interface with the GPU. So I won't be able to show this code that instantiates multiple contexts. But normally, you can call the context function to get your current context. The device is also bound to a context. If you're switching devices, you'll get a different context, because the context, again, represents all of the memory that's been allocated to a single device. With this do block, you can conveniently switch from one device to another device within the same process. There's also the device reset function, which is a little dangerous, which will completely reset the current context. As a result, for example, memory allocation, every CuArray that you've created will have been invalidated. This can be convenient for benchmarking or for other purposes where you want a clean slate before doing things. Generally, there's no need to use this. You can also inspect some of the configuration that is associated with the current context. For example, the way how CUDA will use caches can be configured, the way how shared memory and registers are distributed can be configured. We can configure all this for different devices as well, but again, not relevant to this cluster. If you call a wrong device, you'll get an error. Streams are another very important abstraction. A stream is a stream of execution on which all operations are ordered. And by default, in Julia, we use a single stream per task. And this is also why if you launch two kernels in succession, you don't have to synchronize in between, because those two kernels will be executed on the same stream. And as a result, execution will be in order, and one kernel will depend on the other. The same happens with all other API calls. If you do a memory copy after a kernel, there's no need to synchronize, because the memory copy will have been ordered on the stream after the kernel. However, sometimes it may be interesting to create new streams to overlap execution. In the next notebook, I'll show how you can do so using CUDA tasks, using Julia tasks, again, because every task has its own implicit stream. But if it would be needed, you can create new stream objects. So if you just call stream, you get the task default stream, but you can also create a new stream. It is then important to pass that stream object to every function that takes a stream input in order to execute that function on a different stream. For example, we can do so with the stream argument to add CUDA, which will launch a kernel on a different stream. And just to illustrate, so here I have my task local stream, and here I'm at async, I'm creating a new Julia task. And on that new task, I'm also querying the stream object. So here you can see that every task gets a different stream because the pointers in there are different. Every Julia task gets its own stream. Similarly, if we synchronize, we will only be synchronizing the current stream, and that's important. If you want to synchronize a device, you have to call a different function, namely device synchronize. By default, synchronization is only going to synchronize the current stream. It's also possible to configure the stream. For example, every stream is associated a priority. You can change priority of a stream, or you can create new streams with a different priority. In case you want to fine-tune how operations are overlapping. However, as I'll notice later in the next notebook, it's often better to just use Julia tasks to launch operations on new streams, because every operation within a task will be implicitly queued on the task local stream instead of creating your own streams and doing your own stream management. But this is just to show that we offer all of the functionality to make that possible. Another building block in Julia is events, which can be used for timing purposes. And this is, for example, how the addElapsed macro in CUDA works. We create 2 events, we record one, do some operation, we record the other, then we can synchronize the event and determine the time elapsed between both events. And again, this is how CUDA.addElapsed and other benchmark utilities work. You can do so manually if you have the need of doing some fine-grained time measurements. So we can compare with addElapsed gives, and as you can see, this execution time is very similar because it uses the same mechanism. Events can also be used to order operations. For example, here I'm showing that the current stream is idle. We have a tool to allow you to launch arbitrary CPU code on a stream, which can be used to perform an operation after a kernel finishes, for example. However, an alternative is to use events. We can create an event and see that the event is immediately done because there was nothing happening on the stream. So that event immediately got scheduled and executed. And we can show that if we record the event again after an expensive operation, it won't be done. So that mechanism can be used to order operations after some expensive work, or to create fine-grained hierarchies of work that depends on work, even potentially in other streams. So this can be very valuable if you need, for example, here I'm waiting on a dependency from another task, namely a dependency that was submitted on another stream. So this can be used because tasks are using their own streams, so in a way they are completely independent from another. Using events, you can have one stream, one task, wait on the input of another task. And this is a fine-grained alternative to having to do device synchronization all over the place. Because naively you might think, I'm doing something expensive now, in order to depend on this from another task, I need to fully synchronize the device. That may be expensive, and with events, you can do much more fine-grained synchronization between otherwise unrelated tasks using unrelated streams. And finally, another interesting feature are computational graphs, where if you do a whole bunch of operations, as we've discussed before, submitting each of these operations has a certain cost associated with it. Kernel launches can be expensive. An alternative for that is to capture those operations in a computational graph, and then you can easily replay that graph multiple times, and the launch time of the graph will be lower than the sum of the launch times of the individual operations. So here we've recorded these operations in a graph. I can show that this didn't mutate the data, so I started with zeros, I added 1 to 3, I got 9, I captured my graph, I still have 9. Now I can instantiate my graph, execute it, and we get the expected result. The problem is that, of course, oftentimes you don't want to record the exact same thing happening. There's slight difference. The inputs might change, for example. And if we would do this, we can do so by calling the update function on our graph given a specific previously instantiated execution. So here we've recorded a different graph, and we are going to update the instantiation we did before using this new graph, which uses a different input. And as a result, we can reuse our previous instantiation and execute that without having to re-instantiate our graph, because this instantiation is the expensive part. The problem is that we cannot re-instantiate we cannot update an existing instantiation if the differences are too large. For example, here I've changed the dimensionality of the input. And as a result, it says that, sorry, I cannot update that previous instantiation. It has been invalidated because there were too many changes to the computational graph. As a result, what we have to do is we have to create a new instantiation in this case. To make that more convenient, CUDA.jl provides an add captured macro, and that add captured macro will automatically check whether the graph needs updating, whether the graph needs reinstantiation, and it will do that all automatically for you. So this can be a potentially interesting way to lower the cost of launching many kernels in a for loop by, again, aggregating them in a computational graph for which the launch time should be lower than the original launch time of the individual operations. Again, always benchmark this. To be honest, I've almost never seen a speed up from this, but development has continued, so nowadays, and given your specific application, it might be a valuable tool to speed up your launches. And there's many more functionality that I haven't covered here. I just covered the basics from which I think that are relevant for a application developer level question.
What does it cost to create graph? Because memory.
Yes, no idea, sorry, no. I have to measure that.
And it is memory cost linked with the size of the kernel and the size of the data.
Sorry?
It is the memory cost of the graph linked with the size of the kernel and the size of the data of the kernel.
Probably, but I wouldn't be able to tell, no. There's an introductory blog on graphs on the NVIDIA technical blog. So if you're interested, have a look at that. I'm mainly focusing on how to use it from CUDA rather than when to use it.
No, I was asking that because so I read like maybe a year or something, and I did an implementation. So I had mainly a small map of multiplication. And it appeared that when I created the graph, the memory just exploded, and I wasn't able to do the graph. So yeah, that's why I wanted to make sure it's okay.
Yeah, sorry, no additional experience with that. Some functionality in CUDA we haven't wrapped in convenient high-level wrappers, as I've shown before. But again, you can always still use the C functionality. So if you need something specific because of porting stuff, use the C functionality. One thing to note here is that we are interfacing with the driver API and not the runtime API. The difference is often that the API is slightly lower level, but it's exactly the same functionality. The difference, however, is that almost all of the driver functionality is prefixed by CU, while the runtime functionality is prefixed by CUDA. So if you're porting code and you see a C call CUDA something something, and you don't find in CUDA.jl, replace CUDA by Q, and you'll find a similar function either in the CUDA.jl source code or in the driver API documentation. And it should be straightforward to port one to the other. Another interesting lower level library that we have wrapped is NVML, which is the NVIDIA management library, which can be used to manage your device and the hardware. So recall that devices give you a CUDA device iterator, while NVML has its own representation of a device, and you can go from a CUDA device to an NVML device by its UUID. So you can construct an NVML device passing the UUID of the CUDA device. And now we have an NVML device representing the same device, but with some interesting functionality. For example, we can see how much watt the device is currently consuming, what the utilization rates are, or which processes are currently using the device. Again, this can be useful if you want some nice charts or progress bars for your application to show how many electricity you're consuming. Any questions on the CUDA library support? then I'm going to advance to the second notebook I have here on memory management. So in this notebook, I want to explain or focus on two things. On the one hand, how do you manage GPU memory? How do you instantiate some more fine-grained CuArrays? And on the other hand, I also want to focus on some Julia-specific considerations, because Julia, being a garbage-collected language, has some consequences on how to ideally manage GPU memory. So first, we have a couple of convenience functions that can show you what the total memory on our device is and what the available memory of our devices. However, we've had quite some people file issues about, hey, you're consuming way too much memory. I do this operation and available memory is always 0. You have to know here that by default we are using a memory pool, a CUDA memory pool, which means that the available memory might be completely gone, but that doesn't mean that all of that memory was actively in use. It may just have been cached by the memory pool. And for insights in that, you can call the memory status function, which gives you both the effective memory usage, which is a device level memory usage, and then the memory pool usage. And there you can see how much bytes were reserved. And there's functionality to purge the reservation pool by calling CUDA.trim. Generally, that shouldn't be needed. But so if you're doing memory management, always know that we're using a memory pool. So if you look at Task Manager, or if you're just looking at these functions, you might get a wrong in ID of the memory usage characteristics of CUDA.jl. That said, Julia is a garbage collected language as well, meaning that if an array is not used anymore, that doesn't mean that it will be freed immediately. It has to wait for the Julia garbage collector to come by and collect that memory. And that memory will always still be marked as actively in use until the garbage collector has come by. We automatically invoke the garbage collector every time that we run into an out-of-memory situation. So generally, it shouldn't be needed to automatically invoke the garbage collector. However, there is one interesting tool which you can use to inform CUDA.jl early on that memory can be freed. And this is you can do so by calling the unsafe free function. And with this, you don't have to wait for the garbage collector to come by and free your memory. So it's a bit of a hack, but it can be very crucial if you have an application that allocates lots of temporaries and you know at the end of the scope that all of those temporaries can be freed again. If you're not using the unsafe free, then you're essentially waiting or relying on the garbage collector to free up that memory again, while in this case, we're helping the garbage collector a little. It's an unsafe operation, so you should only do so when you absolutely know that this memory is unsafe. Nowadays, we have some guardrails in place, so you'll get a nice exception and not a crash when you're accidentally using this memory afterwards. But generally, a safe pattern to do so is, for example, here in my function, I'm allocating some work area. That work area is only required for that expensive operation, and then we know the work area cannot escape this function, so this is a safe place to unsafe free it. Now over to memory management from a CUDA perspective. So until now, I've always just been allocating CuArrays, either using the Cu function or using the CuArray function. This allocates so-called device memory. So that's memory that has been reserved on the device and takes up space on the device. This is identified by a type variable in the CuArray type. If I allocate an CuArray by just doing Cu, we can actually see in the output that this is a device buffer. It is possible to request different memory either by passing a different memory type as a type variable to the constructor. So here I'm specifically requesting a one-dimensional single precision GPU array, but one that resides in unified memory, and you can see that reflected in the output. A more convenient way is by using the keyword argument unified equals true to the CU function. It also supports host and device. Device equals true is the default. The behavior of all of these memories is slightly different. So we're at this point still defaulting to device memory. Device memory is the most straightforward memory, performance-wise, behaviorally. For example, if I allocate some memory, you can see the available memory drop by 1 gigabyte, which is expected because here I allocated a 1 gigabyte array. Device memory we can derive a device pointer from, which is what all of the library wrappers and so on do automatically. So if you call a CuBLAS function, it will request a device pointer, and that works. However, we cannot request a host pointer. And this is the error that you would see if you use device memory, accidentally or not, with a CPU library, in which case a host pointer would be requested. Now, unified memory behaves differently. So here I allocate unified memory. Unified memory does not change the device usage. Unified memory is a memory that's allocated on the CPU and which will automatically be paged to the device when the device accesses pages of that memory. And that's very convenient because, for one, it allows you to store more data than your GPU actually has available, given that you have the RAM memory on the CPU, of course, to store it. But it also allows us to derive both a device pointer and a host pointer. And this is interesting because, as a result, we can efficiently use this CuArray from the CPU as well, making it possible to pass a unified CuArray to, say, a C library doing things on the CPU or doing scalar indexing. And to make that really convenient, it's even possible to create an array object from a CuArray, but only when the CuArray is backed by unified memory, of course. If it were backed by device memory, there's no safe way to create a CPU array from a GPU array. Nowadays, the inverse is also possible. So you can wrap a CuArray around a CPU object. And as a result, obviously, we get a unified buffer, because this cannot be a device buffer. We have some CPU memory. Once we wrap a CuArray around it, we will register that CPU memory to become unified memory so that the GPU can access it, and then we give you a CuArray object. So this, again, is very convenient if you have a large swath of CPU memory and you don't want or can't copy that to the GPU. Just wrap a CuArray around it. There's a couple of considerations. For one, this is an unsafe operation because the resulting CuArray does not keep the array object alive. And vice versa, if you wrap an array around CuArray, you have to be careful to keep both objects alive. Otherwise, you could be using the array while the garbage collector has already collected the CuArray and the memory has been freed. So that's why this is currently marked an unsafe operation, and we expect to be improving this in the future in a way that these lifetimes are coupled automatically. But for now, if you do this unsafe wrapping, you have to be sure that you keep the objects alive as long as you're using one or the other. So let's zoom in a little of unified memory some more. Again, scalar indexing was disallowed when we're using device memory because there's no efficient way to access that memory instead of copying value per value from the device. However, our B array is unified memory, and we can access that efficiently from the CPU using scalar iteration. Unified memory can also be interesting to access one GPU's memory from another GPU. For example, here, I cannot show it, but the code should be clear. On device 0, I allocate a temporary array. Then I switch to device 1. If this were device memory, there's no way to use that memory safely because memory is bound to a device. We could use explicit copies. We could allocate new data on device 1 and then do a copy CUDA.jl will automatically try to make that an accelerated copy, for example, using NVLink or using other accelerated buses. However, even easier, we can just use unified memory. If we have a unified array, we can use it on one device and then use it on another. However, note the synchronizations, because unified memory can be accessed by different devices, so on different streams, you have to properly, carefully synchronize when one device is done writing to the buffer before you access it on another device. There's no automatic synchronization happening here. The same happens, by the way, when you wrap a CuArray with an array or vice versa. If you're accessing it from the CPU, the GPU may be accessing it concurrently, so you don't have to do the synchronization between different devices manually. There's no implicit stream ordering as there is when you just do a single stream of operations on a single GPU. What I didn't describe yet is host memory. That was the third type of memory. Host memory seems a little strange, but it becomes clear when you look at a regular memory copy from Julia allocated memory to a CuArray. We can see here in the stream that our copy took as long as it did for the copy to finish, even though we called an asynchronous copy method. And this is because if you're copying from the CPU to the GPU, it's possible that the CPU memory could be paged out at any time that the process did something else, which is unsafe because behind the scenes the copy was still happening. And as a result, even if you ask for an asynchronous copy, CUDA will perform that copy mostly synchronously because it cannot reasonably assume that this copy could safely proceed in the background. And this is where host memory comes in. If you allocate host memory, the host memory cannot be paged out by the operating system. And as a result, the asynchronous copy can truly behave asynchronously. So here the CPU doesn't have to wait for the copy to happen. It can just queue up the copy, continue executing something else, and of course at the end we're synchronizing and waiting for the copy to happen before doing something with it. Allocating host memory again can be done by passing the host equals to the Cu function or by setting the mem.host type to the CuArray constructor, but there's an easier way. If you have existing host memory, you can use the mem.pin function to pin it and make sure that it cannot be paged out. And as a result, pinned memory can be used to accelerate large memory copies. If you're noticing that you want to be able to perform other work while the copy is happening in the background. And this may be very useful if you're in the initialization phase of your memory, allocating and copying memory over, and you don't want to wait for the copies to finish before doing some other work, either work on the CPU or maybe work on a different task on the GPU, which is then using a different stream. So in effect, you might on one stream be copying data, using it afterwards, and at the same time on a different stream be doing some kernel computations or initializing some other memory. So this pattern makes it possible to have much more executing concurrently even on a single GPU. And for that, you need to pin the memory such that the memory copy can really happen asynchronously. This isn't free, of course. Pinning memory, it's not a zero-cost operation, and if you pin lots and lots and lots of memory, it will degrade performance. So you shouldn't be pinning gigabytes on all of your memory, because in effect it means that the operating system cannot page out that memory to disk, and your CPU, your actual memory usage on the CPU side will increase.
Why instead of staying in the memory and then
That's what CUDA does behind the scenes. So the question was, why not use a staging buffer that's pinned and copy into that and then copy to the GPU? That's in effect what CUDA does behind the scenes if you do an asynchronous copy. If you request an asynchronous copy of unpinned memory, it will maintain a buffer of pinned memory, copy into that, and then on a different thread, it will do the actual asynchronous copy.
But there you have the staging buffer, right? So you copy to this big buffer.
Yes. I'm not pinning a copy here, I'm pinning the original. So here, I'm allocating my memory.
That is the solution you propose. But if you don't do that, then as you described, you will get the staging buffer and internally.
That will happen transparently in the background, yes.
Why is CUDA not taking your buffer, pinning it, and then asynchronously unpinning it after?
Because that might have a detrimental effect on system performance. Because you may be copying lots of memory, and if it would start pinning all that memory, it might affect your performance much, much more than when it just maintains a single pinned buffer that it can reuse for different copies. It's not an option to just go in and pin all your memory. I mean, future, or actually currently releasing architecture and operating systems will improve this, like the Grace Hopper architecture will make this a better situation, making it easier to more transparently do this, but currently you need to rely on pinning the memory in order to avoid these asynchronous copy. Lastly, I want to briefly talk about texture memory, which is another special memory type that has certain operations accelerated. Specifically, interpolation between pixels is hardware accelerated, which can be beneficial to some operations. So for example, here I'm going to use a couple of Julia packages that provides me with a very nice test image. CUDA.jl only supports very plain data types. So for example, here we have the type isn't mentioned, but this is a fixed point RGB value that is not supported by the texture system. So we have to reinterpret this image to simple RGBA bytes. We can do this using this reinterpret invocation. And now we can create a texture array from that memory and then create a texture that's bound to that texture memory. Here I'm passing the normalized coordinates equals true, which means that within a kernel we'll be having to access the image with coordinates ranging from 1 to 0, which can be a convenient way again to write kernels that work on all kinds of inputs. So for example, let's write the simple kernel, which is going to warp my coordinates using the sine function, and ultimately let's visualize, well, this is the definition. Let's then visualize the image by reinterpreting the data back to the element type of the original image, which will make it possible for Jupyter to visualize the result. And there we go, a warped image. And you can see here at the borders that it replicated the border pixel. This is also one of the nice features of textures. If you index out of bounds, it will perform a certain border mode based on what has been configured. For example, here the default configuration is to just repeat the border pixel, but it is possible to for example, here I'm using the address mode border, which is going to introduce a very clear white pixel where I'm indexing out of bounds. It's also possible to warp to the other round and so on. There's a couple of different address modes. CUDA.jl also defines interpolations, as I mentioned, because that's the thing that textures are also good for. Interpolations between pixels, that is when indexing in between pixels, are going to be hardware accelerated. By default, the hardware only supports a couple of simple interpolations, namely nearest neighbor, which is the default, and linear interpolation. CUDA.jl, based on the hardware accelerated linear interpolation mode, also defines a cubic interpolation mode, which as a result is then also hardware accelerated. So I can demonstrate that, for example, here in this kernel, just to illustrate, I'm not using normalized coordinates anymore, so that's why I'm expressing my new coordinates in terms of the size of the input, whereas before I was just using a value between 1 and 0. I'm going to launch this kernel. Oh, I didn't define it. And now we can see that the image isn't, it's slightly blurred. So if you compare to the previous one, here we have, maybe it's not really visible on the slide, but here you have the jarred edges. You can especially see it at the bottom, while here you have nicely interpolated, this using cubic interpolation. Again, all of this is hardware accelerated. Even for non-image workloads, it can be convenient if you need to sample a mesh, it'd be 2 or 3 dimensional, having to use interpolation to get values in between coordinates.
So that's all hardware accelerated. How much faster is your mind? This experiment we want to do.
Yeah, and the question was what the performance advantages of hardware accelerated interpolation. Haven't measured it. Sorry, no idea.
And how big is the picture?
How much what?
How big is the picture?
There is a limit. You can also query it using device attributes. It is limited and it's smaller than you're also limited in the amount of textures you can instantiate. So there are some additional limitations on using the hardware texture units. That's true. All of those can be queried using device attributes, because it depends on the compute model, on the generation of the device. And finally, I'm going to quickly talk about some more advanced copying methods. And for that, we're going to use array memory, which is a representation of pitched arrays, where you can encode the stride of the elements as part of the copy method. For example, if I allocate some zeros and allocate some ones by customizing the destination pitch and the starting position, we can do a copy that ends up in the middle of this dense array. And these kind of copies can be, again, convenient when you're dealing with, say, halos or borders or I don't know what. That's it for the memory management notebook. Any questions? The final notebook is on concurrent GPU computing. So here I'm going to zoom in on what I briefly mentioned in the first notebook in this session, namely that much GPU state is task local. So in Julia, if you write code, it's executing in the main task. However, it is possible to create new tasks using the add async block. For example, here I'm creating 2 tasks with add async. Surrounding those by add sync will make Julia in your main task wait for both these tasks to finish executing. So this pattern can be done when you want to spin off some work in the background. Now, crucially, this doesn't use threads. This is cooperative multitasking on a single thread. Julia will automatically switch away from blocking operations to another task that's ready to work. For example, here, I have a sleep, and that sleep is an ideal point to pivot away to a different task. So for example, here in the output, you can see first we have task 1, which is the operation that waits. Then when we hit the sleep, we pivot to another task, which then prints task 2, another operation, and then finally we go back to task 1. So this is not multi-threading, this is multitasking. In effect, what happens behind the scenes is that instead of this sleep, Julia is going to check whether the sleep has expired, and if not, it's going to call the yield function. And the yield function is yielding your thread of execution to other tasks which are ready in the scheduler to operate. And there's lots of functionality that's yielding by default. For example, sleeping is, if you do network activity, if you write to disk, if you write to standard output, because it's only going to flush once in a while, then this might take a while. At that point, it's going to yield execution to other tasks. So those are the basics of concurrent execution. Now on the GPU, this might not seem very interesting because in effect, GPU computing is already asynchronous. Namely, if we launch a kernel, that's going to return immediately, which means that the GPU is asynchronously behaving in the background while we on the CPU side aren't waiting for those operations to finish unless we call the synchronization function. Now, if this weren't the case, then every GPU operation would wait for the GPU to finish executing, and we wouldn't be able to saturate the GPU, hence bubbles in the execution stream. And this, of course, goes back to the application optimization notebook, where we have to avoid synchronization where synchronization isn't necessary. However, there's still some operations that are still blocking. For example, the synchronization operation is going to block the current task until the GPU finishes executing. Similarly, copying memory from the CPU to the GPU, as I mentioned before, if you're not using pinned memory, that takes a while. The CPU has to wait for the GPU to finish that operation before it can continue. Now, since CUDA 3.0, which is a year ago now, we've implemented these blocking operations, so the memory copy and the synchronize, in the same way as I showed the sleep operation to work. It's going to submit the operation, and then it's going to yield, so that other tasks can execute. For example, here, well, I think I forgot this. Let's try again. Here you can see that task 1 started by submitting GPU operations. Then it hit the synchronization, at which point we print wait for GPU results. And then it should have switched to another operation. See, because trying again, scheduler differences can affect how this code in fact executes. But here it shows that we in fact switch to task 2 to perform another application, then we switch back to task 1. And this is of course where pinned memory becomes important, because pinned memory is an operation. Without pinned memory, the call within CUDA itself is blocking in the C library, so we don't have the opportunity to switch to another task. Here, there's no opportunity for us to yield, because it's really waiting for a call into the CUDA C library to return, and that's another reason why using pinned memory may be so important to maximize the potential of concurrency in your application. Now with that, there's a couple of opportunities. So we now have the ability to execute CUDA code concurrently, because every task has its own state, and because blocking operations are implemented in such a way that they yield. But then the question is, what do we do in the meantime? You might use this opportunity to perform some work on the CPU. So you might, on one task, do GPU work, on the other task, do CPU work. But this isn't actually as straightforward as it is, because if we're doing something computationally intensive here on the CPU, there's no opportunity to yield, because the CPU is doing computations at all time. And you can see in the output here that the expensive CPU task begin, and only then we did the GPU work. So again, this is not executing concurrently. Now, one workaround there is to add an explicit call to yield in your function to make sure that the CPU code can periodically allow other tasks to operate. However, overlapping CPU with GPU computation is not what I would recommend as the prime use case for this concurrent execution capability. What's more useful is the ability to overlap multiple bits of GPU work, and I'll demonstrate that coming forward. But first, the only way this can safely work is if every task isn't trampling over one another. So if we were using a single global stream, then the work you submit from different tasks would still be ordered, would still be a single stream of execution, so the work wouldn't be overlapping. And in order to avoid that, again, coming back to what I showed before, but re-emphasizing it, we're using different streams on different tasks. So on the main task, I'm using a stream ending with 460, and on this temporarily created new task, we're using a different stream. And this makes it possible for operations to, in fact, overlap when they're submitted from different Julia tasks. And this extends to other operations, for example, the cuBLAS handle that I've mentioned before. The handle will be different on every task, and every handle will be configured to use its own thread. Again, here you can see that the stream used by cuBLAS is different on each task. This, of course, also makes it slightly trickier to do synchronization between tasks. For example, here you might expect I'm allocating A and B on my main tasks. I'm multiplying A by B. Then on a different task, I'm calling synchronize. And lastly, I check whether my current stream is done, and it isn't. This means that the synchronization call was in effect, it didn't work. And that's because it synchronized a different stream, because it was executed on a different task. And this is, for example, where the events can come in handy, because it allows you to express dependencies between different streams, in this case, between different tasks. A slightly more subtle but similar case is where if we allocate memory on our main task, A and B, random memory, then we fire off a new task to perform the matrix multiplication on, assign the result to C, and then we inspect the result on the CPU. And as you can see, our computation is invalid. C does not equal A times B. And that's because at the point that our nested task began computing the matrix multiplication, the memory, in fact, had not been properly initialized on the main task, again, because operations are stream ordered. And the crucial thing to do here is to always synchronize at the point where you're producing the data, not at the point where you're consuming the data. If we would put a synchronization in this task, it wouldn't have helped because it would have synchronized the wrong task. We have to put the synchronization around where we produce the data. If you cannot do that, there is a workaround. You could call device synchronization, which is going to synchronize all streams. But that is an expensive operation. So it is much better to do fine-grained calls to synchronize where you produce the data and where assumptions are made that the data will be ready from that point on. Or, as I mentioned, you can use events. Here, I'm creating two events, input ready, output ready. I'm creating on my main task the inputs and recording the input ready event. And then on my subsequent task, I'm waiting for that input ready event. Computing the multiplication, recording the output ready, returning it, but at this point, I'm returning an array that has not been initialized. Oh, where's my... Did that just disappear? Ah, there it goes. And finally, on my main task, I can wait for the output ready event and be guaranteed that the data will be available. So concurrent execution is powerful, but you have to take care making sure that the data is not accessed invalidly. Now, at this point, you might wonder why bother? so much complexity? Well, this is why. For example, here, those matrix multiplications can overlap with one another. So even expensive, well-optimized operations like the CUBLAS matrix multiplication can overlap with one another based on the properties of your device, based on the properties of the input, but nonetheless, if you have much work to queue up and the work is in fact independent, consider using tasks to get more usage out of the GPU, essentially. For example, we can do so with the batched RMSE implementation, where we did so in a for loop, but in fact, every iteration is fully independent. So we can put that in a task. And as a result, we can see that some of the kernels will have overlapped. Overlap is, it's not great, but nonetheless, I mean, there's still some overlap opportunity. As you can see here, some of the kernels overlapped with one another. So in order to squeeze out some more performance, especially on more and more powerful hardware. On older hardware, it'll be easy to saturate the GPU. But now that the hardware is becoming more and more and more powerful, your kernels might just not be heavy enough to saturate the GPU, and it may be required to have multiple workloads executing concurrently to fully utilize the GPU. Another use case can be conveniently using multiple GPUs, because again, every task has its own task local state, so every task can be using its own device. And that's also a convenient way to safely use with multiple GPUs. Here you can see that my multiple tasks are executing in parallel because of the work being submitted concurrently from different tasks. Otherwise, it would have not been possible in a single task to safely switch devices, or at least it would have been tricky. And finally, you can also use this for multi-threading, and this is a better way when you want to do concurrent CPU-GPU work, because then in effect the CPU work will be operating on a different thread, which won't ever block the GPU work or the GPU task from executing and submitting work. And in Nsight, you would then be able to see multiple threads getting created and every thread using the CUDA API separately. Again, lots of building blocks might not be relevant to you, but if you want to get the most out of the GPU, concurrent computing can be very relevant. And that's the end of the final notebook. Sorry for rushing this through, but I think we have some 15 minutes left or so for questions. So in case anybody still has some, I'll be walking around and then we'll be off for lunch.